ready.
But I think in the harsh world, harsh world that's to come. Those will be those days.
Well, we'll just change it to Imperial Center for Inference and Climate Change.
Well, you don't have to be that restricted. There are more than just climate.
You said chocolate on the right.
But I see.
Okay. Hi, everybody. So I think we're going to start on time with today's session dedicated to common analysis challenges. And we'll start with Alan Evans, which will tell us about new statistical methods for future experiments. Go ahead, please.
Okay, thank you. So this is my brief. The conference is from Planck to Euclid, but let's start by going back slightly further to WMAP. And so this is the WMAP temperature correlation function. So what you notice about it is that the data is the black line here. And the best fitting theory is the green line here, lambda CDM. So it's clearly a very simple problem. It clearly works, fits extremely well, and we're done. So applying the scientific method of taking the data, finding the best fitting theory is an easy process. Clearly not, right? So these data are perfectly consistent with this, and why is that? Well, the reason is that in order to do the inference on here, you need to understand very, very well what the probability of getting this data set is, given that the expected theory is down here. And it's not just chi-squared, right? So, in fact, Evstathiou wrote a paper on this. Not many people know that. So what is the issue? It's the challenges that we have going forward are quite large. Moving from the CMB to late time universe data is a challenging prospect. The two sorts of things that we can try to do, one is to characterize the statistical properties of the data that we have, and the other is to learn from it, to infer things from it. And characterizing has its own advantages. If we, for example, measure power spectra and so on, then those quantities, especially if you do them in, as Ruth was saying, in terms of observable quantities, then those things survive even if the cosmological model that you're going to use to infer changes. So those are quantities that essentially just characterize the distributions and can be useful in their own right and, as I say, survive the changes in theory. But most of the time what we're trying to do is to work within the context of a cosmological model and try to infer something about the cosmological model, or sometimes to compare different models and to contrast them. So I'm going to spend most of the time talking about the second of these, where we're doing inference. So I'm going to take a emphatically Bayesian approach where we'll regard information as the state of knowledge. So for some notation, the model is M, the parameters of the model will be theta, the data D, and any prior information is I. And the ultimate goal of any scientific experiment is to get the posterior, and this is the object that you want. And once you've got this, if you've got this or a sample or a set of samples from it, then basically you're done. That's the logical outcome of the statistical analysis of the experiment in the context of doing parameter inference within a model. These are strictly conditional on the model and any prior information, but I'm not going to carry these M's and I's around. Okay, so that's the goal, and the question is, can we calculate this thing? For the CMB, it's an easier prospect than it is for Euclid and LSST and SKA and so on, for reasons that I'll explain. The first step is to use Bayes' theorem and then write this in terms of a likelihood and a prior and an evidence. And the first challenge that we have is, what is the likelihood? typically, before that we'd have to decide what data we're going to use, and typically what is normally used is a set of summary statistics, which may be estimates of correlation functions or estimates of power spectra and so on, but not always. But the challenge then is to know what the sampling distribution is. So sampling distribution and likelihood are used somewhat interchangeably. Likelihood means keeping the data fixed and regarding this function as a function of the parameters, which is how it's normally used. The sampling distribution is the other way around. What's, for a given theta, what distribution of data do you expect? And I think that's the question that you have to always be asking when doing statistical analysis. We generally devise some statistics, some summary statistics, and then make some assumptions about what this function is. But you really have to ask yourself the question, do we know what this likelihood function is? And Planck and others have put in a lot of work to do this in the CMB. We have to put in equally as great work in doing this for late-time physics. And the challenge is that it's typically a very high-dimensional probability distribution, and it may not be easy to write down. In fact, it very often isn't. So normally what we very often do is to assume that this likelihood is a Gaussian function, which may or may not be a good approximation. Usually we do a hand wave and say, well, central limit theorem, we're averaging over some large number of quantities, and so it should be Gaussian. And we rarely stop to question that, but we should. But let's run with it now and see what the challenges are even within the Gaussian likelihood approximation. So this is the Gaussian function. You've probably seen it before. It's dependent on two quantities, the mean and the covariance, and that's all you need. And for the CMB, at least the data that you're working with to start with is very well described by Gaussian data. So why is this a challenge, even with Gaussian data? Well, one is that very often we can work out what the mean signal should be with simulations or with theory, but calculating the covariance function is not necessarily a trivial task, particularly if, as is typical, that the data that you use are two-point statistics, because then the covariance function depends on four-point functions, and those are not necessarily easy to compute, except for the case of Gaussian fields. Sometimes one can calculate an analytic covariance matrix, but very often one has to simulate it. And this brings certain challenges. One is that the estimated covariance matrix can be made unbiased, but one development that was realized some years ago is that the inverse of the covariance matrix is then not unbiased. So you can correct for it with the so-called Hartlap correction. Better is to recognize that given that you have an estimate of the covariance matrix, the true covariance matrix is a random variable. It's a random object, which is constrained by the fact that you have a measurement of it. You don't know what the covariance matrix is. There's some uncertainty on it. So the correct thing to do in a Bayesian way is to marginalize over the true covariance matrix, conditioned on the fact that you have an estimate from some simulations. And that's what Eleanor Selentine did. And it modifies the likelihood to a slightly different form. You have to change one line of code. So that's all you have to do. It's just as easy to compute. But one of the challenges of this is that if you do this with simulated data, is that you may need to run a very large number of simulations in order to get a good covariance matrix. In fact, you absolutely need to have at least p+2 simulations, where p is the number of summary statistics that you're using. Otherwise, you can't even invert that matrix. There are some other things that you can do, but this is basically the story. Now, the challenge for future experiments is that if you do the sort of traditional methods of calculating, say, or estimating shear correlation functions in different tomographic bins, for Euclid and LSST, one's probably talking about 10 tomographic bins. There may be, you may estimate correlation functions of the order of 10 or 20 in each tomographic bin, and you've got all the cross correlations. The number of summary statistics that you would be dealing with grows quite rapidly, and you may have something like 10 to the 4 summary statistics to deal with. So that means the number of simulations you need to run gets extremely large. impossible, essentially. And it's even worse than that, because if the covariance function varies with the cosmological parameters, which at some level it will, then you may have to estimate this correlation function basically everywhere in parameter space, and then it becomes unfeasible, prohibitively expensive. So one solution is very obvious, really, that P is too large, so let's make it smaller. That's easy to do. Data compression is a trivial exercise. You just throw away 90% of your data, or 99%, but that's one way to do it, but it's not going to be necessarily a very good way. So the challenge is to do this data compression in a way which preserves as much information as possible. And for the CMB, that's absolutely possible, because we know that it's very close to a random Gaussian field. So you can do massive amounts of data compression. Not necessarily going to do the analysis this way, but going from the time-ordered data to the map to summary statistics, you can reduce the data set essentially without losing any information. And you can, in the context of a model, even go still further to reduce this to the number of parameters. But what do we do when we don't have Gaussian data, or we have a more complicated situation, and we want to do the data compression in a way which is which loses as little as possible? And there's some work we did quite a long time ago for a completely different reason, which is becoming useful again. Well, it's always been useful, but useful in a different context, which is to use this Moped algorithm, or variants of it, which have been developed since. And the idea here is that we can, perhaps quite remarkably, reduce the size of a data set, depending on what the form of the data is. It doesn't work for everything. But if you can reduce the size of the data set from whatever size it started at to the size of the list of the number of parameters that you have in the problem, which is not obvious that you can do this at all. You can do it at the level of the Fisher matrix, that you can do the compression in such a way that the Fisher matrix gets preserved. So it doesn't guarantee that out in the tails of the likelihood distribution it's going to be the same. So they're not summary statistics they're not sufficient statistics, rather, in the statistical sense, but they're pretty good. And there's been developments since then to generalize this massive data compression down in different contexts, including using machine learning techniques, which Tom here has worked on. So I won't go into details, but just to say that if you do this massive amount of data compression, you can lose very little information, and it really solves the simulation problem. And I think data compression is something which we're going to have to deal with and employ in future experiments. Okay, so let's have a look now at the assumption that goes into many of the things that we do, which is that the statistics that we use are Gaussianly distributed. So this is some work that Eleanor Selentine did looking at simulated CFHT lens data. So these are correlation functions of shear. They come from averaging pairs of ellipticities in bins. There are lots of them. You might think that the central limit theorem says that these statistics should be Gaussian distributed. So she checked and had a look, and this is a statistic which don't need to go into details, but if this is all of the summary statistics arranged in some order, and looking at a quantity which, if they're Gaussian distributed, should just look like noise, like this. But this is in fact what they look like. So this is a case where the central limit theorem would probably lead one to think this should be Gaussian distributed, but it's really far from that. The question is, does this matter in terms of the inference? If this is somewhat non-Gaussian, does it feed into our parameter inference in an incorrect way or not? That's an open question. Next issue is we typically look at 2-point statistics. We heard a little bit about 3-point ones yesterday from Michele and others. But if we stick to the 2-point functions, then is that going to capture everything in the CMB? The answer is yes, but for late-time physics, the answer is certainly no. So we have to go beyond two-point statistics for sure. Question is how to do that. Should we just look at more summary statistics at higher level? That's one way to go. I'll argue that there are other ways in a moment which capture that information in a different way. Okay, so how do we deal with non-Gaussian likelihood? So this is the really big challenge, I think, for the future. The distributions that we're dealing with are significantly non-Gaussian. One way, which Florent Leclerc will talk about later, is to use likelihood-free approaches. So I just want to have a slide or two on that before going on to something else. Essentially, the idea is to use simulations heavily to try to get to this posterior, which is the ultimate goal of the experiments. And so one way to do it is basically to generate as many simulations as you can and keep only those that look exactly like the universe. And that, in a sense, is what you would like to do, but it's clearly impossible. If you do it naively, it's extremely inefficient. You end up running large numbers of simulations, almost all of which end up not looking like the universe. So one has to be a little bit more circumspect about saying that the simulations match the data. You can perhaps demand that some summary statistics are the same or close to the same as the data. So the way that one can do it is to try to approximate the joint distribution of parameters and data. So let me just illustrate this with a highly simplified version where you have one parameter and one datum. So this joint distribution basically specifies everything. If you can estimate it using some kernel density estimation methods, probably, by running a lot of simulations, you populate this plane, and then you run some KDE on it, and then you have some approximation to this joint distribution. Then if you cut it at a particular theta, then that gives you the sampling distribution, the probability of d given theta in this direction. But you can also fix the data, the observed data, and go in this direction, and that would tell you what the posterior is. So that's an interesting way to go, and we'll hear more from Florent this afternoon or this morning. So the question is which statistics to use. What should we use for D? We cannot do this with 50 million pixels in the observed domain. So you can't do this in high dimensions. There's some limit, which I suspect is probably round about 20, that you can do this sort of KDE in sensibly. So you have to compress. If you have, say, 10 cosmological parameters, you really have to compress the data down to a similar sort of dimensionality before you do this. And here, Moped and its variance, I think, is the way to go. It's really the only way that you can compress the size of the problem down to a dimensionality that you can really do this with. So that's another role where this sort of massive data compression, I think, will play a significant role. Okay, so how can we avoid using summary statistics at all? So that's the traditional way of doing things. Perhaps sort of stepping back and thinking, well, what would we really like to do if we could, is to go all the way from theory to the things that we really observe at the final stage. Rather than messing around with the data and compressing it into summary statistics. As I say, for Gaussian fields, then you can do the compression without losing anything very much, but we're not dealing with that situation anymore. So what we'd really quite like to do is to calculate the posterior given the data that we're really dealing with and not some modified version of the data. And you can do that by using Bayesian hierarchical models. So these are relatively challenging, but possible and increasingly possible to do these computationally. And it includes all of the information, 2-point and everything else is all in there. So why is this a challenging problem? And I think perhaps the best way to think about it is that when going from theory to what you actually observe, if you just think about the levels of variability, where do you have some variables or some random variables in the problem in that chain of reasoning between, if you're doing generative models, between theory and generating some synthetic data, or going the other way, inferring from data going back to the theory. And there's variability at all sorts of stages, and some of them in using traditional techniques are quite difficult to deal with, but in BHMs, then they come in generally rather naturally. So for example, if we were going to have a generative model of some present-day cosmological data, then we would start with some cosmological parameters, get the power spectrum out, but then in generating a realization of the universe, there's some randomness there in the phases and the amplitudes. If we're talking about galaxies, then there would be some stochastic bias, possibly. There's Poisson sampling. In case of weak lensing, there's shape noise. There's all sorts of variability. If we're looking at photometric redshifts for Euclid or LSST, for example, then those redshifts are uncertain. There's some variability there. We don't know the truth. There's also the general problems of missing data, bright stars obscuring bits of the sky, selection effects, which can be quite complex, measurement errors, and so on. So there's variability all over the place. And if you try to do this with, if you, for example, use a summary statistic that basically just takes what you have and does some transformations to it, you end up with an object whose sampling distribution may be very difficult to compute. So Bayesian hierarchical models allow you to include these effects and basically anything that you can throw at it. You can add in many things. So this is, for example, this is I think a CFHT field showing just some of the effects that you have to deal with in terms of the coverage of the sky. So masked regions, for example, are very easy to include. You basically just give those pixels infinite variance, and that's extremely easy to do. So if you can do this, then this is in a Bayesian way, this is the principal way to do it, because you can include all of the uncertainties at these levels of variability and make sure that you have correctly marginalized over uncertain variables along the way. So let me just give you an example, a very simple example of a BHM, which is to, let's say that we have, we generate a noisy cosmological field. So we start with some power spectrum C, say, draw it from some prior distribution, and then we generate some random numbers and generate a field, S, by Fourier transform or whatever, add some noise to it to get the data, D, and that gives us the D. So how do we do this experiment with a BHM? Let me just go through a very simple BHM. The goal, as always, is the posterior. Probability of theta given D. This we cannot write down as a simple expression, but we can introduce latent variables, which are the true values of the map. So we measure noisy versions, but there is an underlying truth. We can introduce those as hidden latent variables that we don't measure directly and marginalize over them in order to get the posterior. And then what we can do is to use Bayes' theorem to turn this around, and then use the rules of probability to divide these probabilities into other things. So the first one of these, the probability of the data, given the field values and the parameters of the model, well, this doesn't directly depend on the parameters of the model. In most cases, it's just measurement noise, say, or shape noise that depends on S only. And this one we can split into two parts. And it splits the problem up quite nicely into, in this case, 3 different sorts of probability distribution. There's a measurement part, there's a theory part, the probability of getting a map given the parameters of the theory, and then a prior. And the whole point of these Bayesian hierarchical models is that we write down the probability that we want in terms of some conditional probabilities that we have some hope of being able to, of knowing. And in cosmology, we're often in quite a good situation with that we do have ways of getting these conditional probabilities. Okay, so this is, I think, the way that ideally one would like to do it. The challenge of it is that this becomes a very high-dimensional thing. It's all very well to say, yes, we just marginalize over all possible maps. That is a non-trivial statement. Okay, so it's a very high-dimensional space, So you may have something like 10 million different map values. So you're marginalizing over a 10 million dimensional space. So that is possible to do with Hamiltonian Monte Carlo or Gibbs sampling or some more recent techniques as well, maybe profitable. So let me just show you, this is a somewhat old slide now, but show you some simulated data where this is simulated shear data. This is a simulated map. We add some noise, we mask out some regions, and then infer the posterior by drawing samples. So we can't get the posterior analytically, but we can draw many samples from it in this very high dimensional space, in this case about 500,000 dimensional space. So each of these frames of this map are draws of the map. So you can marginalize over the, if you want the map, you can marginalize over the cosmology. Here, in this case, you can get the power spectrum by marginalizing over all possible maps. You have this joint distribution of maps and parameters. So you can recover, for example, the E-mode power spectra to levels well below the shot noise. Each additional thing that you include adds levels to the hierarchy and makes it more computationally more difficult. So I'm just about to wrap up. So just to say that the posteriors that you get out can be highly non-Gaussian. They can be whatever you like. You're not making restrictions on that. You can add in extra layers. These people are all working on this problem. So adding in these other levels of variability, let me just mention one, which my student George Kyriakou is doing at the moment, which is to reanalyze the kids' Viking data, looking at the redshift distributions. So the redshift distributions are also random variables. We don't know what they are. They're not fixed. So we make some measurements of colors or do them in different ways. So here, these what you see here in red are basically summaries of the samples. He draws samples of the redshift distributions. So you can marginalize over the uncertain redshift distributions in a principled way. And what you see is that you get some modest differences from doing it in other ways, and how this feeds through into the tension between Planck and kids, we'll see. You can do this in large-scale structure. So this is Florent Leclerc and Dugesh, also here, part of the Aquila Consortium, who do this with large-scale structure. My time is up, so let me just leave the conclusions and just say that there are severe challenges, I think, to do with the non-Gaussianity of the fields that we're dealing with and the very high dimensionality of the probability distributions that we have to deal with. But there are some techniques which are proving to be possible to apply. And so I think we can solve this problem. But I think we have to recognize that in addition to making the experiments really good, which they are, and the theory, which has to be developed because there are uncertainties there, you have to improve the theory, you have to improve the data, but you also have to improve the connection between those two. So don't spend 10 years designing the experiment, taking the data, 5 years developing the theory, and then ask your student to calculate chi-squared. Do something a bit more sophisticated. I'll stop there.
Thank you, Alan. We have time for a few questions. And can I ask Shirley Ho to come down so that she'll be ready for the next talk?
In cosmology, what we can calculate are statistical expectation values, right? Ensemble averages. And what we can measure are realizations of those if we have the right model. So, and what we then usually do is we calculate again, or we determine certain statistics by assuming ergodicity, that we have statistical homogeneity and isotropy. But we can never calculate data, right? Because that's always a realization. So shouldn't we compare apples with apples, expectation values with expectation values, or as good as we can measure expectation values, of course?
Right, so I think, I think you can compare data with data. I mean, I think the BHM does, it essentially moves the likelihood right to the data level. So So you can, if you have models which will generate realizations of data, and you know the error distribution of the data, then I think you can, I mean, you do compare apples with apples, yeah. But I think with the summary statistics, there's nothing wrong with that. I think because you can do the same thing, your data is just different. It's just your data is some processed version of what you actually measured. In a sense, it always is some processed version. But the question is, you know, what is your data? What is the sampling distribution of those data? And that's, I think, the point where, with the late time universe, that's a quantity which is not often very easy to do because of the high dimensionality and because of the non-Gaussian nature of the fields.
There's a question here.
So I'm obviously very interested in the redshift distributions you showed. Can you, for somebody who's not that familiar with these models, summarize what kind of information goes into the simulations of these redshift distributions?
So these are based essentially on BPZ. They're template-based methods. So the data that goes in are the fluxes in the various bands, the 9 bands of optical and infrared. So that's the data. So the issue is that here we're not, because we don't use individual objects to do the science analysis, we're not actually interested in the probability distributions for individual galaxies. But what we are interested in is what their redshift distribution is. So what we obtain is our samples of the joint template, magnitude, and redshift distributions. So it's a 3-dimensional histogram that comes out. This is work of Boris Leisted, Hiranya Perez, and Daniel Mortlock, I should have referenced. Essentially, you treat it as a stats problem. You say, what's the probability distribution for those 3 quantities, conditioned on the fact that we have some magnitudes, some fluxes for a whole bunch of objects.
I think we're running a bit late already, so I think we should go to Shirley Ho's talk. She's going to tell us about learning the universe with machine learning. Oh, too much, sorry.
Hello, everyone. First of all, thank you for the organizers to make this room cooler than I expected. I just arrived yesterday, so this is my first 20 minutes of 25 minutes of the workshop. This is amazing. It's way cooler than outside. And making it possible, of course, to bring the whole crowd here. And so if I have made any mistakes or make the talk really hard to understand, it's all my fault. The organizers did a wonderful job to cool the lecture hall, especially to the level that we can actually listen to the talk. It's impressive. Thank you, Sophia. Thank you, Francois. I'm going to talk about something kind of, if you were in the Euclid meeting not too long ago, you probably heard the same talk, so you can just kind of go to sleep. But if you haven't, I'm very excited to tell you something that we've been doing. There are 2 parts of the talk. The first part is using machine learning to sort of like do a full information to regression to the cosmological parameters that we all love and care about. It could be astrophysical parameters. The second part of the talk is try to understand why that works. And it became sort of, can you map the universe? Can you make the n-bar simulations of the universe like 60 million times faster? So that was the second part of the talk. So try to pay attention to 2, and then I will try to make sure it's kind of useful and entertaining. But all the work are done by the students and the postdocs. Obviously, the faculty don't do anything these days. The students who just graduated, Siyo Hei, who followed me from Carnegie Mellon to Berkeley, now to Flatiron, she just defended like last month, like late last month. Yingli, who's a Berkeley postdoc, actually also IPMU. Yu Fang, who's a Berkeley postdoc. Paco, who a lot of you probably know here, is at Flatiron. Wei Chen from Facebook Research. Simon Renfenbach, machine learning faculty at UBC. Barnabas Postos, long-term machine learning collaborator of mine at Carnegie Mellon. Alan Joe Sarmer at Flatiron. And Julia Oliver, who was a student with us at machine learning, now at Washington University as a faculty. Jeff Snyder, who's a machine learning faculty also at Carnegie Mellon, Ling Price, who was a postdoc with us now at Amazon Research, and Sebastian Formentel, who's a postdoc with us before and now at UNAM as a faculty. So without them, none of this work is possible, so make sure all the credits go to them. I'm just delivering the talk. All right, the nature of dark matter and dark energy, arguably two most interesting open questions in physics these days. Maybe not true for some of the people here. Maybe you care about astrophysics more than cosmology, but arguably two most expensive ones. Given that LHC is spending billions of dollars, Euclid is also fairly expensive. So what do we do with these very expensive experiments? We collect some of these data. So for us, it's the cosmological data. I'm a little bit biased towards the larger structured data, even though my thesis actually did a lot of CMB work. So this is a picture that if you plot all the Sloan galaxy, actually Sloan 2 even, and that's the larger structure that you will observe from Earth. So what do we do with the usual current cosmological larger structure analysis? A lot of times what we did is that we go, so they would have been an animation if you actually would have a PowerPoint, but PDF is great. You go from cosmological distribution of the matter or the galaxy, which is unbiased tracer sometimes, or sometimes biased tracers of the matter in the universe, depending on what tracer you use, to some summary statistics. Alan gave a really excellent talk, so you know all about summary statistics and what other method you can do about them. But usually we're still at this level. We go from distribution of something to summary statistics compared to different theories. That's why those two lines, the red and the blue. And then you have constraints on dark energy or dark matter or any other things that you care about in cosmology or astrophysics. This could be on neutrino masses also. So can we do better than what we have done before? Alan had given two really excellent sort of pathways to do something we've been always doing with sort of likelihood, MCMC, and I'm trying to show sort of the third way. Also slightly crazy way because this is what faculties do when they get tenure. 2016, actually, we started realizing that there's a lot of interesting things happening in the world of deep learning. One of the first things that happened that kind of really reached the media is that it beats the gold champion of the world by using deep learning when it was just training by itself. This is the 5 human Joseki common corner sequences. They were discovered by AlphaZero when it basically plays itself. So it was a Nature paper in 2016. Then deep learning and protein flow in 2019. This is actually a few months ago. If you read it, you realize that if you were given a sequence of amino acids and you're asked to predict the shapes, why is the shape important? Because it tells you what the properties of the proteins are. And then you say, OK, how do I predict the shapes of the protein if you're just given the sequence? So people given these as a competition every year. And the the first runner-up, got 3 out of 43 tasks correct. While Google DeepMind has done 25 out of 43, which is the winner. And it doesn't actually do protein folding. It's not a protein folding institution or anything like that. So I thought that was interesting. This is what people usually use these days to recognize all the pictures on any social media using or for surveillance, if you're thinking a more sinister application for this. This is called something called residual neural net. It's what actually won the 2016 competition in recognizing all the images in a context. So you have an image. There are many things. It's not a postage stamp because it's really easy. But in a very complex and many things is happening, it gives you a probability of every single thing, what it could be. Self-driving car does it. There are many different methods to do this. But residual neural net 2016 went down to percent level error from before, which was very impressive. And that's actually the method we're using in one of our work. So that's why I brought this up. So what did we do? So the first thing we did was just to try to do something kind of crazy, see if it's even possible to use machine learning to do cosmology. We used a simpler setup, which is dark matter simulations in a box. Throw it into something called convolutional neural net. Back in those days, I know those days means 3 years ago in machine learning, that's like a few decades ago in terms of improvement in algorithms and everything. There's only 2D convolutional neural net, so we were just crazy to even try to do 3D. So we did that, submitted to International Conference of Machine Learning, got published. And by the way, for machine learning conferences, the acceptance rate is usually 5% to 10%. So to get accepted is probably bigger than publications sometimes. So then we throw in the convolutional neural nets. This is something that I'm not going to describe exactly, but basically it does a bunch of multi-scale convolutions, and you feed the information, go step by step. And what the final output we want on this far right-hand corner is the cosmological parameter. And the input is just little cubes of cosmological simulations. I'm not dealing with data effects. I'm not dealing with all kinds of things like you can get to the galaxies. This is just dark matter simulation, just to see if it works. So the input training set is ML simulation paired with cosmological parameters. Every one of them, we know exactly what they are. But if you look at it by eye, well, you can go back to the previous slides, you can see that those 3 boxes with different cosmological parameters don't look that different by eye. But maybe a neural net can distinguish them. And we know that 2-point statistics can tell you their difference, 3-point statistics can tell you their difference, but this is we're trying to do everything. Validation step is that you input next set of simulations, but you also have all these parameters so that you can tune something called the hidden parameters, how many layers you use. There's many things where you normalize. So BN is batch normalization. You just normalize the things you feed into the network, for example, whether you do it or not. What kind of pooling method, which is basically saying that they say something called max pooling very often, is that if you have a square image and you divide it into 4 different pixels, do you take the maximum or do you take the average for the next step? That's basically all it means. For the test, you input the n-body simulations without telling it the cosmological parameters and predict with the network that had just been trained and validated. So here's the punchline for the first part of the talk. Ground truth is on the x-axis, y-axis the prediction. And you can see that there's an omega matter in sigma 8. And what I used to do is this power spectrum analysis, which I take these little cubes and I run, basically calculate a 2-point function. You can do, anything, power spectrum, correlation function, doesn't matter. And I compare to our theory predictions up to a certain k because, I can't trust my theory to order infinite k. That's the red dots. The blue crosses is what the convolutional net were doing. So I thought that was very interesting because it's doing better in some of the variables and probably equally good in the other variable. So what's going on? Is there extra information that we can pull out of here other than 2-point function? Because obviously the power spectrum analysis is only doing 2 points. So it also echoes what Alan was showing earlier. 2-point doesn't capture everything, especially the more nonlinear the field is. This is something people know forever, but just proving that the machine learning algorithm is also picking up extra information. But as scientists, we have many, many questions. We can go get a correct estimate of the error. Can we interpret the model learning, machine learning, which is a huge problem in applying anything in machine learning. Actually, in particular, deep learning is very hard to explain to any scientific problems. Or more provocatively, can machine learning interpolate and even generalize from data just like humans does? Because we only have one universe, and we're generalizing all these rules out of this universe, right? And can it do the same thing? If it does, then why? So the first part of the stuff, which is the correct estimate of error, I'm not going to talk about it, but we have published different work. So looking at how to get the correct estimate of the error for using machine learning, and how does it compare to errors we know. So we use CMB as sort of like a data set to look at this. And it actually gets the same error that you would know from like the traditional error analysis for CMB. And that's what you expected, because CMB is completely characterized by a 2-point correlation function. And can we interpret the model learning machine learning? This is what I'm trying to do today. And the last point, which is, can we use machine learning sort of to extrapolate, not just interpolate, but also extrapolate from data like human does, and why? So can we interpret what the model is learning? This is getting a little into the weeds, but hopefully it's not too boring yet. So we want to design the following experiment to learn the difference between analytical modeling, which is on the left-hand side, the stuff we all know and very well, and the full information of ML model on the right-hand side in density field. In other words, for those who do larger structure theory, can we understand what gravity does to millions of particles over many, many years without using computer to simulate the physics, right, step by step? Or even flip it even further down the question line, which is a very similar way to think about, can we use machine learning to skip the entire simulation of a complex physical system, but just go ahead and learn what is happening? So that's what we did in the setup of this experiment. On the left-hand side is the input, which is analytical approximation of the nonlinear evolution of the universe. On the right-hand side is the positions and velocities of all the particles evolved under gravity after X years. Instead of using numerical model as simulations of Newton's law for all these particles over so many years, we want to attempt to use machine learning to learn or interpolate from a large number of pre-run simulations. Simulations we already ran is just sitting there. We call those training data. So here's the setup. We're showing slices of simulation instead of boxes because it's easier to look at, but we are all in 3D. So analytical approximation here for the crowd here, we know it's, I can explain what it is. It's self-divergent approximation. And we want to map it to numerical fields. And the middle model here is something called the UNet. It's a variant of residual neural nets. Exactly why we picked this is actually very interesting because, if I can have a pointer, they have the same size in the input and the output. Usually what you see before is that like a really large things and then you get to like one number, which is like a regression problem. Here you're trying to use the information here and learn something interesting. And you're also still using multi-scale information from the input, which is exactly the problem we want, exactly the setup we want, because our problem has large-scale information correct at the self-divergent approximation. So you still want to bring in all this information in large scales while you want to learn the fact that we are inputting pairs of analytical to simulation boxes, right? So the analytical one tells you what the large scale is doing, and the simulation boxes tells you for each of these analytical approximation, what is the full nonlinear n-body, which adds the information of small scales, right? So the neural net here is trying to get the large scale information and the small scale information that actually won't be as inputs to generate these full n-body simulations. So that's what we try to do. Let's show how well we're doing, because it's a first talk. All right, here's the error. We show the errors in displacement field, because displacement field is interesting because it encodes the velocities and the positions at some level. Our benchmark model, we use TLPT because it's fairly fast, and that's what basically all the surveys were using at some point to generate a large number of any simulations, because you need like 1,000, 2,000 of them to get your covariance matrices. And our ML model, so we want to compare ours to something that's basically fast. And the displacement field is the difference between the current position and the initial position of the particles. The errors in megaparsec over h. Here is what the benchmark is doing. So 0 megaparsec, the maximum error actually in the 2LPT is 7 megaparsec over h. And you can see it's not doing so bad. It's just slightly bad at high density regions, basically where the overdense region is. For the unit displacements, the maximum error is 0.7 megaparsec over h. So it's about 10 times better. And we thought, oh, that's pretty good. It also has this interesting property where at high density region it doesn't do so well. But I think we have found methods to improve it already. So let's do it a little bit more quantitatively, because we just don't stare at pictures all the time. We want to say how well it's doing if I want to simulate a whole universe. We check the following: the average of a Pau spectrum of 1,000 simulations, the ratio to the true Pau spectrum, and the cross-correlation coefficients. And instead of plotting the cross-correlation coefficient, which encodes the phase information, how well the phase is correlated, we plot 1 minus r squared, which is sort of the error Pau spectrum. 1,000 simulations were predicted in 30 seconds. And in our work here, that was just published in Proceedings of National Academy of Sciences, we use fast PM as the truth, which is fairly fast. But we have done all this work with the full numerical simulations, which each one of them take 1.8 million seconds, CPU seconds to run. So it's about 60 million times faster. And what we did here is that we tried to show how well we're doing with Pau spectrum. So if you just squeeze your eyes really hard, we want to be as good as basically truth, which is the green line. And the orange line, which you can barely see peeking out at the really, really end of it. If you divide them out, you can see the orange line is peeking out from 1. 1 is being perfect. And that's what 2LPT is doing. And that's the noise Pau spectrum, where also the phase correlation is doing extremely well compared to the 2LPT at fairly large scales. We can push it to higher K, but this is at K equals to 0.7, where also hydrodynamic stuff, gas astrophysics will also come into play. There are 2 other papers that we finished recently that actually learn, using machine learning to learn to map from the dark matter simulations to hydrodynamic simulations, that not just including CDMs. So take a look at those if you're interested in pushing further into higher K. So we checked the 2-point function. Seems like the model is predicting well. You ask, well, 2-point function is easy because you already input self-divergent approximation. So we want to do a little bit harder, so we did 3-point function. For those who don't work on 3-point function, it's just basically 3 points in sky, as its name. As a triangle, it's formed by 2 sides, R1, R2, plotted here. And the angle is basically characterized by these multipoles. L equals to 0 to L equals to 8. For those who really don't care, this is just a picture we want to reproduce. This is what the benchmark is doing. It's the 2LPT. Looks pretty good. I mean, you can see if you're matching just looking at these two, especially with early sleepy eyes, they look exactly the same. The fractional residual is plotted here, so we'll try to show you how well it's doing and how well we're actually doing pretty well too. Our fractional residual is about 10 times better than what 2LPT is doing. And mind you, it only takes 30 milliseconds for each simulation to be predicted, which is also faster than 2LPT by a significant amount. So can we interpret what the model is learning in the machine learning? Well, we kind of flip this question around is, can I basically just simulate all these interactions instead of just using analytical approximation? And yes, we can. And more provocatively, can machine learning interpolate and generalize us like humans? And if it does, then why? This is a fun part of the talk and also really short because we don't know the answer why this is the case. What we did is that we input analytical approximate maps of different cosmology from 0.1 to 0.5 instead of 0.3, which is all our training simulations. All of our training sets are in one single cosmology with different initial conditions. So Planck plus BAO, basically. So they all have omega matter equals to 0.3. And we throw in input, which is Saldohage approximated map, this cube that is basically all these quantum fluctuations get kicked and just freeze the initial acceleration. And basically particles just go like swimming by each other. That's the inputs, but with different cosmological parameter. That's very important. So how different are they? Here's the density field. That's the displacement field with the vectors. And you can't really see very well with the color, unfortunately. But basically, when this universe is about 50% or 60% difference, here is about 20 to 30 to 40% differences. So there's significantly different distribution of particles and velocities. So can the model extrapolate instead of interpolate? For those who are curious in machine learning, this is a big question. Basically, if you're teaching the machine learning algorithm to recognize between cats and dogs, you can differentiate between the two. Can you differentiate from an elephant? That's sort of the question you're asking. Or basically, if you can recognize a bottle of water and laptop, can you recognize the table? So it's a zero-shot training, or something people are very interested in is called transfer learning or meta-learning. We did not use any of those methods. We just simply take the trained model and throw in a different input. So can this learned model extrapolate and predict simulations that do not have the same cosmological parameter as the training set? Not surprisingly, I would say yes, we can, because we check the following: the average power spectrum of the 1,000 simulations, ratio to the true power spectrum again, the cross-correlation coefficients, look at the phase correlations. We have 3 different lines: the solid lines, the long dashed lines, and the short dashed lines. And let's see. The solid line is the truth. It's basically plotting the average of what the training set is, well, what the truth is, which is omega matters to 0.1 or 0.5 universe power spectrum. Long dashed line is the prediction using machine learning, which has the correct input, which is omega matters to 0.1 or 0.5 universe, but the model was trained with given omega matters to 0.3. And the short dashed line is what 2LPT is predicting. Here's what we got. Again, it's extremely hard to read, which is, I guess, good and bad thing. The solid line is what we want to reproduce. The long dashed line for all models are completely hidden under the solid lines, which means ML prediction is doing so well, it's basically impossible to pick out from the line 1, which is perfection. Omega matters 0.1, 0.3, and 0.5 are the 3 different colors. And here's the power spectrum of the errors. Also doing better than 2LPT. So what happened? We don't need to overlap the training set with the test set. We didn't explicitly use any transfer learning or meta-learning or any of those. We did not retrain our model, basically. We did not do anything interesting, except we changed the input. Is there an overlap of information somewhere between these universes? That's the first thing I immediately asked. I suspect there is, but then how can we prove how much of that is causing this extremely good extrapolation, and how much of this is this the possibility that the nonlinear evolution, basically the fact that you input particles going like this, and the fact that the particles interact gravitationally in sort of like etherealized, that part is learned by the machine learning for one single type of universe, which omega matters to 0.3 in Planck plus BAO parameters. How much of that is sort of not so dependent on the fundamental cosmological parameters that we're changing? Maybe the universe is fairly simple, so that generalization, extrapolation by the network is easy. Some machine learning people is like, well, maybe it learned the physics completely. We humans figure out, well, actually mostly Einstein and a few others, figure out what these equations are supposed to be from one single universe after all. Or maybe I'll finally get famous, my possible climb to fame. These are two people I care a lot about. The first one is my husband. Hopefully you're not very interested in him. The second one is Alice Honnold, who recently free climbed the wall in El Capitan without ropes and made it into a movie called Free Solo. He got very famous recently. And they were climbing together like 5 years ago, and I thought, that's my possible climb to fame. Like, my husband climbed really well. I'm like the photographer taking all these awesome pictures. But maybe it's machine learning the physics of cosmos, compressing learned model into physical laws, or maybe it's discover the new laws of nature, possibly through machine learning, possibly with other methods, with how we understand making simulations really fast. Who knows? So the conclusion here, there's immense hype and probably immense potential for machine learning to, in everything field today. In machine learning, I really mean deep learning these days, ranging from playing Go, image recognition to healthcare. I mean, I can raise any examples that you will be quite impressed with. We may be able to use machine learning to help advance physics and astrophysics. In this talk, we showed two different applications. One is that we use a deep neural net to predict cosmological parameters with some successes that's better than just 2-point functions. We can start using machine learning to be an approximate simulator of any complex system with large number of particles. So mind you, before our work, the largest number of particles people have been able to use machine learning to predict is 12. So the fact that we've gone to like millions is pretty impressive. But also relatively complex systems like our universe. So we need to understand what's happening under the hood before fully deploying machine learning or deep learning, because it's what people always complain is a black box. We have actually done a lot of this work, but it's not published yet, to how to basically probe the network that is learned how to generate numerical simulations from very simple analytical approximation. And it's got some interesting results, which I hope to show you some other time. Furthermore, physical data sets, physical problems actually in particular, could be interesting for a machine learner, because we are the only field that has model for high-dimensional data sets. So you can think of healthcare, there's really very, very little model that is actually truly predictive model. Neuroscience is probably the one that comes closest. They have some model of the very highly complex system. But Facebook picture does not have a model. NLP, natural language processing, doesn't have a model either. So this might be an interesting playground for people who want to understand how machine learning works also. We have more questions than answers, and that's why it's exciting. I'll take questions from here. Thank you.
Well, thank you for this provocative talk, I would say. So I'm sure we'll have lots of questions.
Hey, nice talk. So I'd like to know, like, for the case when you have extrapolated the omega meta value, how are the initial conditions chosen? Are they same as the other one?
They're independent. They're not the same.
Independent. Okay, that's nice.
They're independent from the training set, deliberately so.
So they are completely different initial condition and different parameters, but it is able to recover.
They're only different by one parameter, though. So omega meta. We tried also AS, also successfully. Yeah. So we haven't tried all the parameters. I'm only saying we tried 2 parameters, which is omega meta and AS.
Thanks.
So we have one here. And then
So it's quite interesting. Hi. The fact that you input, essentially, you start from Salvage approximation, which I think is part of the reason that guarantee the low K parts always have a very good agreement with the truth. But then you're kind of saying that the starting point is from one single parameter, like one cosmology, and then you can predict, essentially extrapolate to something pretty far out. And that does already necessarily infer that the small-scale structural formation doesn't really care about, or doesn't characterize any information at all compared to what.
That's what we thought too originally. Actually, that's what our referee said. It's like, can you check whether the small-scale information depends on sort of the cosmological parameters, such as omega matter and AS. And if you believe second-order Lagrange perturbation theory is a more correct characterization of the universe than subdivision approximation, there's a term that actually that depends on cosmology. So you can actually prove that there is information in the small scale part, which is higher order perturbation theory, that actually depends on cosmological parameters. So you can actually just write down your equation. If you believe 2LPT is a better approximation of the universe than subdivision approximation, then there's an extra term that you actually need to include.
But then it's a bit counterintuitive in the sense that the network doesn't even have the chance to learn about the small scale structure formation, how it depends on the parameter, because it doesn't even know about whether that parameter is a dependence at all, right? So isn't it a bit strange?
It is very strange. I didn't claim I understand it, by the way. I never understood any of this, by the way. Nobody knows. There are many suggestions of how to do this, and we're sort of working through all the suggestions. So I'm happy to take suggestions. We're just working it step by step. Yeah.
Another question there?
Okay, so you said that you are using training data, and actually you're using training simulations for your machine learning. But these are usually based on a specific model. So how do you make sure that you are not missing out on new physics?
Mixing up what? Sorry, say again.
That you're not missing out, you're not missing any new physics, because you have to use a specific model for your n-body simulations.
If I understand the question, is that are we, if we have a really truly different universe than our simulation, then how can we use machine learning to sort of understand the cosmological parameters of the universe, right? So say modified gravity is correct with certain parameter, and I only train the universe with one set of parameters, what do I do, right? This is really interesting because people always ask the same question. If, self-driving car training set doesn't cover all the possible problems, would you kill someone? That's the same question. One thing people really do is call this adversarial adversarial situation where you try to test the basically train model to see how it reacts. So you can do that, which is what the self-driving car people were doing. What we're doing is kind of slightly different here, is that first of all, if you take a set of data, what you want to do is to compare its distribution to probably your simulated data. And you can do it very effectively with something called GANs, generative adversarial networks. So you try to find sort of outliers and anomalies. So at least check that first, like if it's significantly different in some weird ways, so you can check that one first. The other thing, which is what we're kind of trying to do, is can extrapolate to different type of simulations, right? So what we're doing, if omega matter is not 0.3, it's like 0.34 or something like that.
Yeah, but this is not a problem of parameter. It's not a problem of having a different omega matter. It's a problem of having a different theory.
So very extremely good question. If the parameters was very different from what you can extrapolate, or even better, if the parameter is the same but has jumps in it, if there's no smooth extrapolation allowed, what do we do? Very good question. We don't know the answer to it, right? Like what's smooth extrapolation in a dimension that is interesting. There's one thing people are working on that this just came out recently. It's called Hamiltonian Network. And we started to look at that, is that can you sort of generalize along the lines of conserved quantities? So it's very similar to the idea of symplectic integration in the old days. Well, not old days, I guess. In this way we do it, we go along, we do some integration, and you make sure the conserved quantities are correct. So that qualitatively everything still looks okay. You push the errors to the directions perpendicular to the conserved quantities. And people are starting to look at that in machine learning. So there are many ideas. It's a very new field. Our work is like the first one who tried to do this. I'm not saying it solved any problems. We're just working on it.
Okay, thank you.
Thank you. I think we should thank Shirley for the very nice talk. And please, Linda Block is going to tell us about cosmological simulations for large-scale galaxy surveys.
Let's try. Where is the?
It's a put a bit further. I want you at 15 minutes, so you have 5.
Okay.
So you have 20 minutes. Okay.
Oh, sorry.
You have 20 minutes plus 5 minutes question. I
Okay.
want you at 15.
Okay. Is the first one? Yeah. Okay, hi everyone. So I'm going to slightly shift gears now because this is not really statistics, but I wanted to talk about simulations, the role of simulations in large galaxy surveys. So we had already a lot of introductory talks about this, but let me just briefly summarize what how we can do cosmology using large galaxy surveys. So we basically have two ways of probing the density field with galaxies. One is using spectroscopic data, so you have very precise redshift information, and with that you can measure things like the baryon acoustic oscillations and the redshift space distortions. And the other way is measuring shapes of galaxies, and then the statistics of the distortions can tell you about cosmology using cosmic shear. So most of what I will present is related to Euclid, but it's true for any kind of large galaxy surveys where you have a very large number of galaxies and large areas. So in the specific case of Euclid, we will have 50,000 square degrees and 50 million galaxies in with spectra, and 1.5 billion galaxies with shapes. So these are very large numbers. And the problem of modeling large-scale structure observables is that contrary to CMB, we are affected by the nonlinear regime of gravitational collapse. Plus, we are observing galaxies that are biased tracer of the density field, and moreover, they are discrete tracers. So you have shot noise that comes into play. And you also have baryonic processes on galactic and cluster scales that are having a feedback effect on the large-scale structure. So you also need to take care of that on the smaller scales. And finally, as any observations, you have observational effects and systematics. So in the case of weak lensing, we already saw this picture. What we are trying to measure is the distortion of the intrinsic shape of galaxies. And by the way, this is highly enhanced just for showing the effect, but what we are trying to measure is much smaller than this. And then when you start to apply all of the observational effects, this is what you are actually seeing. And in the case of Euclid, what we are doing is slitless spectroscopy, as Gigi already showed a few days ago. And this means that you take the whole field and you disperse the light along one direction. So if you have two sources that are really close in the direction of the dispersion, then you can have things like overlapping spectra. And then what you're trying to do is just to measure emission lines from the spectra. And so you can have problems like line misidentification. And so what I want to tell you today is that for all of these problems, we need simulations to understand them. Even if you want to model analytically large-scale structure observables, you are still going to use simulations as benchmark. And even if we do very nice machine learning, as Shirley just showed, you still need simulations for training. So this is, I mean, for sure, you are going to need simulations to do large-scale structure. So let me just show you an example of a very computationally intensive task we had to do in Euclid. So we recently completed the science performance verification, which in layman terms, it just means that we want to check that we are going to reach the science goals given the current service specifications. That, of course, they are going to change, as also Gigi presented. So every time you change the survey strategy, you need to check that you are actually going to meet the science goals. So to do that, what we needed was a complete forward modeling of the survey to the best of our knowledge today. And we want this mock galaxy catalog to be statistically compatible with observations. And we also need this to be feasible in a reasonable amount of time. So we cannot really simulate the whole Euclid area using hydro simulations, also because it's impossible with current computers. So we need to use some simplified modeling of the galaxy distribution. So I put here just a sketch of what we do. Basically, it's a two-step process. We start from a halo distribution from an embodied simulation, and then we do some statistical modeling of the galaxy distribution using a combination of halo occupation distribution and abundance matching. And basically, we match our simulated catalog to the luminosity function, the color magnitude diagram, and the clustering as a function of luminosity and color to the data of the SDSS at low redshift, and then we apply some evolution to go to high redshift. And then as a second step, we model the single galaxies in the catalog to get the additional properties that we need, which are the photometry, the spectra, in particular the emission lines, and then the stellar properties like stellar mass and star formation rate. So as I said, we start from an embodied simulation. So what we did is we took what are the requirements for Euclid. So Euclid is going to observe H alpha galaxies in this redshift range from 0.9 to 1.8, and is going to take images of galaxies to H magnitude up to 26. And this is over 15,000 square degrees. So when you take this and you turn it into simulation requirements, so this is a plot where you have on the x-axis the volume of the simulation, and on the y-axis the particle mass, which means the mass resolution of the simulation. So you can probably recognize here some simulations like Mice Grand Challenge and Millennium XXL, so that at the time these were among the largest simulation existing. And what we needed for Euclid was up here. So it's several orders, well, at least one order of magnitude larger than what existed at the time. And this needed to be created from scratch, basically. So we decided, so these simulations are called flagship. So the flagship one is already completed, and we already put galaxies on it. And flagship 2, also the embodied simulation is complete, but we still need to generate galaxies from it. But so we use the currently what is the fastest code to generate embodied simulation, which is PKD Grav 3. And the flagship one used almost the entire supercomputer, and it was one of the top 10 most powerful computers at the time, which is bit-stained. It used GPU acceleration, and despite that, it's a very large amount of node hours. So this is for flagship 2, it's 850K node hours. So if you want to compute CPU hours, it's roughly a factor of 10. So it's like 8 million CPU hours. It's a very large computational effort. And this is only for the embodied part. Then you have to put galaxies on this. So the simulation produced 40 billion halos, which translate into 5.5 terabytes of data only for the halos in the light cone. And then when you naively turn all of these halos into galaxies without doing any observational cut, this translates into 60 billion galaxies, which means 20 terabytes of data. And each of the galaxies have more than 200 properties. So this is already big data. And this is even before we get to the real observed data. So it's kind of a good exercise to prepare us for what we are going to have from data, from real data. Okay. So this required a shift in paradigm on how we deal with this kind of simulations. First of all, the size of the data set became very challenging for standard databases, which means that the queries that you run on the simulated catalog could take hours or even days. And this is not feasible. I mean, if you want to do science with that, you cannot just wait for days to have your catalog. So we decided to use a big data platform to store this data and also to generate the galaxy catalog starting from the HALO catalog. So we needed to rewrite all the pipeline that goes from halos to galaxies in a highly optimized Python code, which is optimized for this particular platform. And because even a few seconds more for each galaxy, when you multiply by 60 billion galaxies, it takes a long time. So you really need to optimize codes. And this required, of course, lots of interaction with software and data engineers. So we are not anymore in the regime where you can give your grad student your simulation and tell him, just give me galaxies. We really need to plan ahead for this. And this is just one example, but I think most of the future galaxy surveys are going to need to do this. So Alan already showed this. So this is another example of how we are using simulations in Euclid. We want to do Bayesian likelihood analysis to get our cosmological parameters. And if we assume that the likelihood is Gaussian, then you get this form here, where here you have the inverse of the covariance. And so there are many ways to get the covariance. You can use internal method, which means you slice your data in subsamples and then take the sample covariance. You can use external estimation, which means you simulate your survey thousands of times and then you measure the sample covariance, or you can try to model the covariance. But so this is the example for the power spectrum. You see this part is easy, and it's the Gaussian part, and it's just proportional to the power spectrum squared. But you also have this nasty term here that depends on the trispectrum, which is the 4-point function, which is really hard to predict from theory. So the route we are exploring now is using simulations and using the sample covariance estimator here. And again, as Alan already mentioned this, if you want your covariance to be invertible, which you need to estimate the likelihood, then you need the number of simulations which is larger than the number of data points plus 1. And also, when you use the sample covariance estimator, you have an error on the estimate of the covariance, which is of this order here. So this also depends on the number of simulations and the number of data points. And so if you have, let's say, a requirement for your relative error epsilon, then you can turn this into a number of simulations. And well, I was more conservative than Alan. I put here 2,000, but it's true that this can get more like to the order of 10,000 or even more. So we cannot do this with embodied simulation, or at least it would be really challenging, especially if you want to have realistic simulations. As I showed you, it's 8 million hours just for one simulation. So you cannot really do this with 10,000 simulations. So what we are exploring now is using so-called fast and approximate methods, which are just approximations to the full embodied simulation to produce halo distributions. So we did a comparison of some of these methods. At least we try to cover all the classes of methods that are around. And to do that, we compare to a set of embodied simulation, which is the Minerva simulations. So you have here, this is the particle mass and the box size for the simulations. And for the approximate methods, what we did is that we matched the initial conditions. So we reduce the error in the comparison because they have the same initial conditions. And then we study different observables, which are the two-point correlation function multipoles and wedges. And then we have power spectrum multipoles, the bispectrum in real space, and the monopole of the bispectrum. And then since what we are interested in is the error on the cosmological parameters, we propagate all of this through likelihood analysis, where we fix the signal, but we change the covariance to the covariance of the approximate methods. And since we are interested, this was done for galaxy clustering, we are measuring the Alcol-Paczynski parameter and the growth, plus bias parameters that are considered nuisance parameters in this case. So what you normally do with simulations is just you have initial conditions, you bring them forward using gravity in embodied simulations, then you end up with a final density field at the redshift you are interested in, and then you find the halos in this density field, and you end up with a halo catalog. What this approximate method do is approximate one of the two steps or both, or they go directly from the initial conditions to the halo catalog without even going through the density field. So we have one fast PM method. PM just stands for particle mesh. Is a numerical method that it's used also for normal embodied simulations. But in this case, what this code does is that it uses Lagrange's perturbation theory to solve for the large scales, and then uses the particle mesh part only for the smallest scales. So you can go from the initial condition to the density field in just around 50 time steps instead of thousands that you normally use for embodied simulations. And the halo finding is exactly the same that what you would do for embodied simulations. Then we have two what we call predictive methods. We call them predictive just because they need to be calibrated just once, and then you can use them for whatever cosmology you want. In this class is Pinocchio and PicPatch. So what they do is just they use a collapse model directly from the initial conditions, and they end up with a halo catalog without going through the density field. Then we have two calibrated methods, which instead needs to be calibrated every time you change the sample. But these are faster because they only use Lagrange perturbation theory to go from the initial condition to the final density field, and then they assume a bias model, which is slightly different for Pachi and halogen, to go from the density field to halos. And finally, we have two assumptions about the PDF of the density field. One is that the field is Gaussian, and the other one is that the field is log normal. And in this case, it's really a simulation. So what you do, from the initial conditions, you do a field transformation. So you transform the Gaussian into a log normal field. So you end up with a density field, and then you Poisson sample the density field to get the halos. So we studied two different samples. You can see here, this is the galaxy where these are halos. So the halo number density and the linear bias, which you see is quite large because of the resolution of the embodied simulation. So we were limited by that. So this is the multiples in the correlation function, and you see that all of the methods, this is the ratio of the error on the cosmological parameters that you get from the approximate method divided by the one you get from the embodied simulation. So basically, this is the epsilon I was showing you before. If you want that your approximation does not bias the error on cosmological parameters by more than 10%, then these points need to be in the shaded area. And you see for the correlation function, basically all of the methods perform quite well. in both samples. For the power spectrum, the picture is quite similar, and here I'm also showing the bias parameters. So you see, in this case, the log normal really stands out, especially in the second sample, and I will go back to this later. And then this is for the bispectrum. This time, this is the same ratio, but as a function of K max. And you see that the approximate methods do quite well, but the Gaussian starts failing very early. So for the bispectrum, we don't have cosmological parameters, but we have bias and shot noise parameters, because this is what is going to be used for, bispectrum is used to break degeneracies in the bias. So that's why we're checking these parameters. This is the second sample. Just a few caveats. So the Gaussian covariance is performing really well, but this is also because to estimate it, we used the average of the power spectrum from the correlation function from the n-body simulation. So basically the Gaussian is, by construction, having the same bias and the same shot noise as the n-body simulation. And then the log normal is, when you look at this is the correlation coefficient, the log normal is performing really bad, especially on the monopole. And what we found out is that the log normal gets increasingly worse the higher the bias. So you need to take this into account if you want to use log normal simulations. Just be careful and check that you are getting sensible results. And finally, these samples that we are studying, they are not really representative of what we are going to observe with Euclid. So the number density is going to be higher, and the bias is going to be lower. So you need to take these results with a grain of salt. So I'll leave you with the conclusions here, and thank you for listening.
Thanks a lot. We have time for a few questions.
Hi. Yes. So all these tests you did here, you compared all these different methods of getting dark matter fields and then halos. But really, there's also quite a lot of unknown in how you then go from the halos to what we actually observe, which is galaxy clustering. And I guess there's lots of opportunity for errors and things in that process. So my question is, how much do any differences you see in the dark matter and halo fields actually corresponds to errors we might get when we're trying to use this for real data, when the galaxy part is probably more unknown? Yeah, well, that's a good question. We don't really know how to go from halos to galaxies anyway. So we can do what we did for the flagship Monk and use a halo occupation distribution. And then there is the possibility that so you can do either two things. You can use the same HOD for all the methods, and then the differences you see in the halos are going to be the same in the galaxy field. Or you can just fit the HOD to all the different methods, which would be more sensible in my opinion, because what you want to reproduce is the data. And then there's a possibility that you can reabsorb some of these differences into the HOD parameters. But yeah, it's a good question. I don't know.
There's a question from Shirley.
Very nice talk. I think this is a very challenging work. I just want to mention there, if you believe some of the observations you have, and say if Euclid will have deep field, in principle, we can use a deep field as a training set for machine learning to figure out what's the mapping from dark matter to galaxies using the actual data. Yes. I mean, I'm saying this is in future, of course, when we have deep fields, and then you can generate as much as possible, very quickly, all this mapping. That's just an idea. Yeah, I agree. I think this is a very promising avenue. What you presented is very interesting. And in fact, we are already thinking of ways to use current data to
to get some information about the mapping from halos to galaxies or directly from between galaxy properties. So you can predict some properties from theory, and then you can relate those properties to whatever you need using machine learning from real data. Yeah, yeah, that's definitely an interesting possibility.
Okay. Well, thank you, Linda, and I would like to thank all the speakers this morning's session. We will reconvene at 11 sharp, and I ask all of the speakers of the next session to please check their talks.
You're free. Thank you.
Malencontreusement, skiant.
Oh, skiant.
Début mars, j'ai eu l'opération. Un mois d'arrêt total, 2 mois de plâtre.
Let's put the posters.
Et à part ça,
Okay. So that no more confusion. Yes.
ouais, enfin, c'est cher. Hein. Il faut être riche pour pouvoir vivre là-bas.
Ben oui, justement, ça tombe bien. Okay, so we're going to start the second session of this morning, and we'll start with Romain Tessier, who will tell us all about precision cosmology in the nonlinear regime.
1, 2, 1, 2. Hi everyone. I'm very happy to be here, and I thank the organizer for inviting me to report on what we worked on the past, I would say, 5 years, 10 years, trying to run n-body simulations at a precision better than 1%, And actually, when you try to do this, you realize that you open a can of worms, and you have to deal with a lot of issues that you never suspected before. And you have to combine them all in order to be able to really run an n-body simulation at the sub% accuracy. And so this is an image of the flagship 2 simulation that was completed a month ago. And this, I think, is one example of such a high precision simulation, and that's only been possible recently because we added several new features that have been explored by many other people in the community. So it's not the first one, but I think it's one of the first time we combine them all into such a gigantic effort. So for example, and I will address these points in the talk, we have massive neutrinos and we have general relativistic effects included in the n-body simulation in a very simple way, and I will explain how it works, which guarantees to have sub% precision on large scales. We have a self-consistent light cone. So what do I mean by that? I mean that when you look back at high redshift, you're deep into the linear regime on large scales. And the idea is that the n-body simulation should match the Boltzmann code predictions at the linear level. And this is actually not easy because the Boltzmann code, they have all the general relativistic effect, the metric fluctuations, all the physics. N-body code, they just have dark matter particles flying around with the Newton's law. So in order to match the two on large scales, you need to be careful. Right? And for example, if you ask someone to use the flagship catalog and to compute the correlation function at very high redshift on very large scales, if you're not careful, it will not match the class or the CAM prediction, which is not acceptable. Right? So the number of particles is, of course, very large. The point here is to have the volume that we need for Euclid, barely. And we need 1,000 particles for a Milky Way size halo, which is one of the requirements for Euclid, which gives you a particle mass of 10 to the 9. So actually what is interesting is that some people say, I'm not one of those, but some people say that we might not need to go beyond that for Euclid. For SK, for example, we need larger volumes, but maybe for Euclid we're done, right? we did the largest simulation that we need, right? I'm not sure it's true because as you see, there is a lot of effects that are not fully converged even at this resolution. Okay, so here is the outline. So I will discuss the current status for the accuracy of n-body codes. I will very briefly discuss how we can include neutrino and general relativistic effect in an n-body code in a very simple way. It's not that simple, but it's relatively simple. Then I will discuss an effect that actually is most of the time completely ignored, but now, and only now actually, since we are dealing with sub% accuracy, we are looking into these problems, which are due to the discreteness effect of the particle grid that we start from, and there have been some recent effort, and there is interesting history here. Then, as a mirror to what was discussed earlier this morning, I will show that it's possible to emulate various cosmological observables using a relatively small number of n-body simulations and deliver those observables in the full cosmological parameter space at relatively good controlled accuracy. And this is what we call emulators. And finally, I will discuss baryonic effects, which are the ultimate nonlinear effect, I would say. And here we are much more in muddy waters, as you will see. But I will try to show you briefly, if time permitting, what we can do now. Okay, so the nonlinear effects play a very important role in cosmology, and there is two very famous effects due to nonlinearities. One for galaxy clustering is that the baryon acoustic collision peaks are shifted compared to the linear regime. So if you try to measure the position of the peak and infer cosmological parameters from that, if you don't include nonlinear effect, it's going to be wrong, and it's wrong only if you need high precision, of course. And the second effect, which is more obvious, is that on small scales, nonlinear effect boosts the power and change the shape of the power spectrum, which of course, has an effect on your inference if you use the nonlinear, the linear prediction on a nonlinear universe. So you can do perturbative theories. You can use perturbative theories on large scales, actually relatively large. They are not so large. And you can say also that at small scales, baryonic effects is a mess, right? So the full predictive power of n-body codes is actually in a relatively narrow window, and they're squeezed on the left by analytical models, or 2LPT, or variance, and on the right, they are skewed by the very ugly baryonic world. And so there's actually a very narrow range of scales where n-body are really ruling everything, right? So I think that if you can control baryonic effects, and I will try to convince you, time permitting, that we can do it, then you need n-body models for smaller scales too. Now, the big questions, of course, there are many, but I have two here. How accurate are those simulations? And actually, accuracy less than 1% is a huge challenge. And how expensive are they? Can we include them in an MCMC chain? No, we can't, right? And it was mentioned several times this morning that they are too expensive, right? And so how can we include then the nonlinear correction in an MCMC chain with enough accuracy, or the same accuracy as the n-body model, without having to run simulations? And that, I will try to discuss those 2 points. So that's the matter power spectrum, right? So that's the main observable I'm going to use this morning, but of course there are other observables, 3-point function, peak statistics, redshift space distortion, you name it, right? But here the power spectrum is shown here, and you see the nonlinear boost or correction here. And I have shown here, just for fun, the effect of varying the neutrino mass, because that's one of the challenges of this simulation, is to include neutrinos. The neutrino mass, you see that you can have a different signature here.
Is that the present day?
Say it again? It's the redshift 0, yeah. That's the redshift 0 power spectrum. And so you see this boost on small scales, and on large scales, you nicely match with the linear power spectrum, which actually seems like, okay, everything is fine. Actually, no, because the linear power spectrum is actually a very complicated beast, right? All these effects. Okay, now a very brief summary on n-body codes, for those of you who don't know. What you're doing here, you're solving the Vlasov-Poisson equations using a Lagrangian description of phase space. And actually, for those of you who are not aware, that's not the only method. There are other methods out there who are trying to solve the same Vlasov-Poisson system without using particle. But so far, I would say it's the most competitive approach. But it's not necessarily the most accurate, right? The problems of n-body methods are, of course, quite obvious. Finite box size. Beyond the box size, you assume it's periodic. So you have finite volume effects, right, which are not necessarily only cosmic variance, can be very nasty nonlinear effects. You have a finite number of particles, obviously, and you have finite force resolution in the gravity, right? So those are the 3 challenges that you need to tackle in order to design your simulation and make sure that it meets the requirements that you have in mind, 1%. So now this is a list in historical chronological order of techniques. So I'm not going to go through them, but the point is that today we use methods which are at least theoretically of order n. So if you have capital N particle, then big O n is the cost of those very modern methods, right? And there are 2, the multigrid method and the fast multipole method. And actually, when you analyze them, you realize they are very similar, right? So that's typically what you see. So if you plot the number of particles used in the simulation versus the date, the year of the publication, you see that these different types of n-body methods are basically dominating each decade. And now we are in the last decade where we have multigrid and fast multipole. And we are approaching, of course, we are at the trillion particle scale today, right? Okay, so now all these codes now, how accurate are they? So what we did a couple of years ago was to make a very simple test. We gave 3 groups the exact same set of initial conditions. So you have, in a cosmological model, very well defined, you have a particle position that you start with. And then we asked 3 codes, picadigraph 3, that was mentioned earlier, gadget 3, which is kind of the oldest of the 3, and Ramses, which is a multigrid AMR code. And we run the same exact initial condition, same particle position and velocity distribution with the codes up to redshift 0. And we compare the power spectra of the 3 different codes. And so that's basically an assessment on you know, what are the systematic effects at the level of n-body codes. And in gray here, the gray area is this 1% goal that we have, right? So you see that on large scales, they are basically agreeing. So they all reproduce the same linear regime, right? Which is good news, but which is not that easy to get, right? And so there is a transition scale, k equal 1, that sometimes mark the transition scale for nonlinearity, right? From deep nonlinearity. And then it starts to look uglier, right? And actually, so if you believe that in the group 2 together means they are right and 1 alone in a corner means it's wrong, then Gadget is wrong and the other 2 are right. But it's not that easy, right? Maybe Gadget is the only one to be correct because the other 2 have some kind of similar systematic effects, right? So that's a bit of a worry because we are outside the 1% target here, right? So Gadget 3 is, as I said, is a relatively old code. So now there are Gadget 4, which is more accurate, and the test hasn't been run yet, but I'm sure it will improve. Now, just to give a little bit of hope here, recently, in last year, Garrison and collaborators, Daniel Eisenstein, for example, was there. They redo the same exact test using the Abacus code, which is yet another code with very different choices, which is, by the way, faster than Picardie Graph 3, right? Because it was said earlier this morning that Picardie Graph 3 is the fastest code in the world. I think Abacus is, but they use very, anyway, you can ask me questions about that later. But the good point here is that Abacus seems to fall into the range where Ramses and Picardie Graph 3 were, which means that now Gadget 3, this older code, is now really alone in a corner, right? And now there is all the popular kids are in the same spot. So again, we still have the problem that maybe Gadget 3 is the only one to be right. We don't know. But now I would say there is evidence, there is a growing consensus that we are indeed within the 1% gray area, right? So that's the message I want to convey today, okay? Okay, so that's an issue, and improving this is actually very hard. And we probably need to design a bigger test because we may be affected by resolution effects, but differently in different codes. That's an obvious case of you know, an obvious direction. So we need to, but this is already an expensive test with you know, several billions particles. I forgot the exact number. But we probably need to redo this exercise with a larger ensemble of particles and try to see if we can beat down this to less than 1%. So basically the message is 1% at k equal 10, right? So just to nonlinear scales, we are probing nonlinear scales up to k equal 10 with a 1% error, okay? And that's the goal. That was the Euclid requirement, right? Okay, another problem, a nasty problem that n-body simulation has to face is that they are not Boltzmann codes. They are just pure Newton's law evolving dark matter particle. There is no radiation, no neutrinos, no metric fluctuations, nothing, right? And so now if you use, for example, so here there is basically 2 strategies, right, that you can do when you run an n-body simulation. You run class or CAMB up to redshift 100, then you stop at redshift 100, class or CAMB, and then you generate initial condition for your n-body code, and then you evolve the simulation up to down to redshift 0 using the n-body code. If you do this, and here we are talking at very, very large scales, so this is the linear regime, right? So the solid red line is the initial condition here that you get from class or CAMB, and then you evolve it with the n-body code, with the growing factor, the growth factor here of the linear regime D+, and you land on the dashed line because you have evolved this with an n-body code. If you compare now to class at redshift 0, you get the solid green line. So there is a mismatch, right? And it's normal there is a mismatch because there is not the same physics in the 2 codes. So then, and we knew this for a very long time, right? So then the classical solution, right, is to use what is called backscaling. So backscaling is a very dirty trick. You run class all the way down to redshift 0. So that's your initial condition. You then backscale it using the pure n-body growth factor back to redshift 100. And then, So now you have a wrong initial condition, in a sense. But then when you evolve your n-body down to redshift 0 again, then you have the correct linear power spectrum by construction, right? The problem is that now that's the dashed line here. So the dashed line is the backscaled initial condition, which is wrong when compared to class. But when you evolve it with n-body, you land on the right curve by construction, right? The problem is that this is right only at redshift 0. It's wrong at all the other redshift. And it's very wrong at high redshift, and it's now getting better and better, but it's, you know. So here there is a big problem, right? And unless you write a full 3D Boltzmann solver with, 4 trillion particles, how do you do that, right? And so the idea is very simple, is to add an additional field that is generated by class ORCAMB that is linearly evolving according to the correct linear evolution. And this field is used to source the gravity of the dark matter particles while the simulation is running. And if you do this, you have the correct evolution. So you can start with this initial condition and get the correct linear evolution with all the components, radiation, neutrinos, and metric fluctuations included at the linear level in the code. And so that's an example here that was, so the method is described in this paper. And you see, for example, the power spectrum assuming only Newtonian gravity divided by the power spectrum assuming all the general relativistic effect using this technique, right? And you see the different contributions. So, for example, if you include the neutrino fluctuation, then you get the dotted line. Sorry, the radiation fluctuation, you get the dotted line. So you see the effect is at the percent level, right? And on very, very large scales, look at the scales, very, very large scales. Now, if you include the neutrino fluctuation, then you go up to 3%. And if you include the metric fluctuation, then you get the solid line, which is the final answer, right? And redshift 0 is the pink one. And this is with a massive neutrino. So you have zero mass neutrino and massive neutrino models. So of course, now you can ask, and it's a legitimate question, why do we care, right? Because look at those scales, they are huge, right? And the thing is, in Euclid, for example, you will be dominated by cosmic variance. So you might not be able to see those effects with Euclid. Maybe, I mean, it's been discussed, right? Maybe with clever tricks you might. But for SK, you will clearly be in that range. And moreover, if you generate a mod catalog, you really want to have these effects included so that your collaborators from the Euclid simulation are not coming shouting back at you saying, what, I don't get the proper linear evolution. Right? And so that's what we did for the flagship simulation. And you see here the simulation power spectrum divided by the class prediction, right, at all redshift. And at large scales, we get all these effects completely under control. And what is more important is that those effects are encoded in the light cone that people are going to use to do the galaxy catalog. So that's the difficulty here, right? So you cannot really post-process this as it's one solution to post-process those effects, and it works fine. But here, if you have a light cone with a time variation along the redshift direction, you have to do it during the simulation. And then the nonlinear corrections here are like a boost of power on small scales, and that's the interesting added value of the n-body code is here, right? Okay, one effect which has, I think, has been ignored completely is the fact that particles are always set up on a grid. And it's actually a simple cubic lattice. In condensed matter, that's one of the options for a crystal structure, right? And that's the growth factor, the linear growth factor, as a function of the K mode. And 1 corresponds to the Nyquist frequency, so of the lattice spacing. And the linear regime here should give you 1. So the linear regime is the fluid limit. That's the fluid limit of this problem, right? But here we are not starting with a fluid. We are starting with a crystal structure, right? And you can see here the growth factor for particles, for K modes, with different angles with respect to the grid. And you see that you can have growth factor which are half the fluid limit. So modes in the linear regime in a simulation are growing at half the speed right? And of course, this is happening only close to the Nyquist frequency, right? So if you, for example, if you go down to k Nyquist over 10, then you're back to the 1% target, right? Now, recently, in this paper, they gave a strategy. I have to accelerate. They gave a strategy on how to include those effects, those corrections, into the whole process of n-body simulation. And then you can really mitigate these effects and put them back into the 1% box, which is the target, right? But we didn't do this in the flagship 2 simulation, so we adopted the brute force strategy, which is to put the Nyquist frequency safely to the right, right? So the Nyquist frequency for us is very large, but maybe we could have saved computational resources by adopting this correction. Okay, now quickly, I will describe something which probably is a reply to what was discussed this morning with machine learning, is to use what we call emulators to provide a very fast surrogate model for the nonlinear corrections that can be used in a Monte Carlo Markov chain to estimate the parameters. So what we will provide is an emulator model for the nonlinear corrections. And you see the baryon acoustic oscillation here and the boost as I defined earlier. So here the tricks is really coming from engineering mostly, is to sample the parameter space using a very small number of simulations, a very small number of parameter choice. And for this we use the Latin hypercube sampling, which is a very clever way to populate points in a 6-dimensional, in this case, parameter space. And the strategy is to interpolate the result of the simulation in between those simulation points. And we use a lot of complicated points here. I don't have time to discuss them all. The key point is that with 200 simulations, so that's the number of simulations we have to perform, we can get an accuracy of 0.1%, right? And so when you speak about machine learning, I think you should present results in that metric, right? Because that's what we need. We need to be accurate at the 0.1% level to interpolate results, which are already 1% accurate, right? So that's really the target here, right? And so I think there is a quantitative aspect, which I think is sometimes missing from the machine learning talks. This is very accurate, right? And there is only 200 simulation. 200 simulation. How many simulations do you need to train a neural network? I don't know, but 200 seems like a very low number. So now if you compare to other earlier emulators, you see that this emulator that we published recently is compared to the Takahashi HaloFit model, which is a very famous model. And you see that there is a 4% mismatch, and that's normal because Takahashi's emulator claims a 4% accuracy. Right? Here, it's a most recent emulator called CosmicEmu by Catherine Heitman's group. And here we are at the same level of accuracy, but here you see the problem of the general relativistic effect. Right? On very, very large scales, they don't get the class results accurately enough because they didn't do the correct treatment of these effects. Okay, I'm going to skip the baryonic effects. Anyway, it's better for us, otherwise it's too depressing. And I'm going to throw my conclusions. So my conclusions here is that we are now at the percent level. We can also provide emulators for the power spectrum or for any observables, 3-point correlation function or covariance matrix. We can provide emulators with only a very small number of simulations, right? And I think we start to see in current Winston observation scales and precision. The precision is now enough to start to see those effects, nonlinear corrections, and they are included actually in most of the recent papers. They are included in the treatment, the nonlinear corrections. But as you see, we need to be careful and we need to use the right ones. Okay, I'm done.
Thank you. Thank you for this talk. I'm sure there'll be lots of questions about finite box sizes or baryonic effects. Let's start with here.
Okay. Romain, have you also looked into an emulator for unequal time correlations? You know, power spectrum of C and C prime, delta of C?
With tomography.
Yeah,
tomography.
if you have two different redshifts.
That's possible. I mean, the thing is, you need to define the observable. Then you need to design your experimental design, as we say, right? And then you know how many simulations you need to run. Because you need to know the observable that you're looking at and the target accuracy. And once you know that, then you can design with using simple analytical model, you can prepare how many simulations you need. And then you run the simulation campaign, which is sometimes, it depends, because some observables that you don't need to go to very small scales, right? So it's not necessarily very expensive. For the power spectrum, it is because you want to go to k equal 10, which is quite large, k. But for other observables, you don't want to or you don't need to, so then it's cheaper. But for each observable, you need to design a strategy, and we have the tool to do it very rapidly. Those are engineering tools that, you design this very rapidly, and then you know how many simulations you have to run, and then you need to ask for the computing time.
So when you showed the comparison between the power spectrum out of the n-body simulation with GR effects, with the n-body only Newtonian, the most difference was for lower k, means that larger scales.
Yes.
Therefore, can we, see that the effect on halo mass and like the number density of halos would be negligible? Because
well, the neutrinos have an effect on smaller scales, especially massive neutrinos. They have an effect on smaller scales, right? And here they are included because the neutrino mass we consider now is quite small. They are included at the linear level. And then if you include massive neutrinos, then you can have effects on the halo mass. But for the other effects, I don't know, intuitively I would say no, but you have an effect on bias on very large scales too. But I'm not an expert of that. There are plenty of experts in the room, so if someone wants to discuss that.
So, Roman, you didn't say what the solution was for the, compensating for the grid in the initial conditions. I mean, a long time ago,
for this problem?
Yes,
yeah.
we experimented with what we called glass initial conditions, okay, where we ran gravity backwards to create a sub-random distribution.
So here, in my mind, the best solution is the one that is proposed in this paper, which is very tricky and not ideal by far, right? So the idea is to correct the effect, and the effect can be quantified using particle linear theory, right? It's a very nice theory that was invented by Michael Joyce. So using particle linear theory, you can predict the effect at any redshift as long as linear theory is valid. And then you can try to compensate for the effect for a given target redshift. And then you generate your initial condition at redshift 100 using this compensation. And then you know that at this target redshift, the linear theory will be by construction verified perfectly. And then for the later redshift, for redshift 2, 1, 0, you hope that the time will not be too long for the effect to accumulate. And that's what they did here, right? The red line here is when you adopt this theory to compensate at a target redshift of 5 and then let go without the effect being taken care of anymore, right? But let go down to redshift 0. And you get something which is accurate enough, right? According to this metric here. But if you don't do this, then you get the dashed red line, and you have an effect of 60% at the Nyquist frequency, which seriously, back in the days when I was a student, having an effect of 60% at the Nyquist frequency, I was not shocked. I was saying, fine, let's just put the Nyquist frequency very high to the right. But now we're trying to save computing time, and we try to, and then this technique allows to really fix this issue. But it's not an ideal fix, because you don't really take this effect into account. You just mitigate this effect. Right? You minimize the effect of discreteness error.
Okay. We'll take one last question.
So this is first a comment and a quick question. The comment is, for the emulator work, I think it would be really excellent to combine the observable that are information maximizing, like the work by Ben Wandel and Justin Alsing, to find the right observables to emulate. And I think that will be excellent to combine the two work. A question is, why are you pessimistic about baryons? Because you can't skip over the slide.
Thank you for the question. No, I'm not pessimistic. I'm optimistic, but it's just that baryons are a bit depressing in the sense that they are making a huge effect. They're causing a huge effect on the power spectrum. So this is an example of the baryon power spectrum for the total matter divided by the dark matter only case. And you see that at k equal 10, there is a 20% deficit in this particular model, right? So it's potentially a huge effect, right? Now, the cool thing is that you can try to predict it. You can try to marginalize over it, right? But now, what is depressing is that that's, for example, a plot showing all the current simulations with different physical models for galaxy formation, AGN feedback, and that's what you get. That's all the prediction you get, right? And the one that kind of match observations are the one with the colored line here, right? So we don't understand this very accurately, as you can see, right? Before I was talking about 1%, and look at this mess, right? So that's the pessimistic view. Now the optimistic view is that we might be able to, with a parameterized model, like the one I didn't discuss, you can try to use this parameterized model to marginalize over the parameters and somehow minimize the effect on the final result on the cosmological inference. And that's the optimistic view.
Before we go to Florent and thank Romain, if I may ask a last question to both Shirley and Romain. You said about 200 simulation, and Shirley, how many? And you gave us ideas on how long it took to train and to run new simulation with machine learning. Romain, on your side. So can you both answer those two questions?
I can go first fairly quickly. So it depends what applications we're using, right? So for going to emulate the dark matter simulations with positions and velocities, so the phase-space information, that took 8,000 simulations. That sounds a lot. But then when we map from dark matter to baryonic simulations, so hydrodynamic simulations, we only had one illustra simulation. So that was one. Okay. So it depends what you're doing.
Okay. And Romain, about the time it took to train your emulator?
So it's each simulation is a 40,000 cube n-body simulation, 4,000 cube n-body simulation. And it took like half what the flagship 2 simulation required. So it's a gigantic supercomputing proposal. Yeah. Okay. It's millions and millions of core hours.
Okay, so I would say that's going to be interesting
in the future. Only for 200 simulations.
Okay.
So our training time was 4 hours on one GPU, and our production time was 30 milliseconds.
Okay. Okay, well, thanks for this information. Let's thank Romain, and then we'll listen to Florent, who will tell us about likelihood-free inference from galaxy surveys.
Okay, can you hear me? Yeah, sounds it's work. Good morning. It's a pleasure for me to give this talk and to be back in Paris. So I would like to thank the organizers for this opportunity. So I'm going to talk about likelihood-free inference, especially in the context of galaxy surveys, but this can be actually more generic in cosmology. And I first would like to start by clarifying some vocabulary issues, so some vocabulary considerations. So maybe in my view and in the purpose of this talk, the likelihood, what we should call the likelihood at least, should live at the level of the entire map of the CMB or of the large scale structure. So I wrote the true likelihood with a question mark actually, because it probably should live at the level even of full images and on time ordered data. But let's say for this talk at the level of the map. So this is the case, for instance, with Wiener filtering of the CMB, with Alan Heaven's model for weak gravitational lensing, or a project in which I'm involved, which is called Borg, Bayesian origin reconstruction from galaxies. Here, what it does is to sample the distribution of initial and final conditions linked by a particle mesh model, given observations. And to do that, the likelihood lives at the level of the map, so it's a 256 cubed dimensional Poisson likelihood. So in order to do that, some expert knowledge of the likelihood is required in order to beat the curse of dimensionality and to address these very high dimensional problems. So typically conditionals of the likelihood are required for Gibbs sampling, for linear filtering, or gradients of the likelihood are required for Hamiltonian sampling. So based on what should be the likelihood, now what is likelihood free? So the idea of likelihood free inference is to bypass this need for such expert knowledge of the likelihood by relying only on a black box simulator, essentially. So typically this would be a code written by somebody else, and you don't want to look into their code, but only want to use it to learn something given some data. So typically a generative process looks like this. You have a vector of target parameters, a vector of nuisance parameters. So in the case of maps, this would be in particular, all the Fourier modes, all the Fourier phases of the map. So very high dimensional vector here. This would be typically cosmological parameters or the initial power spectrum. Based on these two, you get raw data from just a deterministic step, and you end up with some compression to get some statistical summaries. So in other words, the likelihood is replaced by a measure of the distance or of the discrepancy between simulated and observed statistical summaries of the data. So let me give an example to make it more concrete. Let's say D would be here full galaxy survey data. The compression would be the estimated power spectrum, or in the case of the CMB, so this would be the CMB map and this would be the pseudo-CLs. And for instance, we can choose delta as the Mahalanobis distance with some covariance matrix here. So this would be the expression for this distance. Note that this is what many people would actually call the likelihood, precisely, or to be more precise, square root of -2 times the log likelihood. But in this vocabulary, this would still be likelihood-free inference. Another vocabulary comment, Sylvia, this one's for you. What is primordial, I believe, depends mostly on your ambition. And since I am not an ambitious CMB cosmologist, but a modest large-scale structure person, I will use the word primordial to mean post recombination. So in other words, you can replace it by initial or linear. So what would be the simplest case for likelihood-free inference? So this would be what is sometimes known as ABC, approximate Bayesian computation. Maybe a more precise word for this would be likelihood-free rejection sampling. So the idea is the algorithm is the following. The idea is to iterate many times the following. So the first step is to sample some parameter theta, target parameter theta from some proposal distribution. So typically this is just the prior here. Then we run the simulation using this black box. So we simulate these data, these synthetic data using the black box. We compute the distance between observed and simulated data here, these dashed lines, for all points in this set. And we retain theta if the distance is smaller than some epsilon, and we reject otherwise. So essentially, we keep everything that happens to fall in this ball of radius epsilon around the true observed data. So this epsilon can be adaptively reduced. This is what's called population Monte Carlo. But still, this algorithm remains fairly naive in the sense that many more simulation will be required than what we can afford for many data analysis problems. So how do we go beyond likelihood-free rejection samplings? So here I can think of two different scenarios that we can be faced with in cosmology. So the first one would be if we want to work in specific cosmological models. So that would mean that we have typically of the order 10 dimensions. And we want something which is very general to explore parameter space. So in this case, what we want to do is actually to reduce the number of simulations as much as possible with respect to likelihood-free rejection sampling. So this is the number of simulations route. Ideas to go down this route, so one has been mentioned this morning already, is to estimate the density of in the joint space of parameters and data. So this is density estimation for likelihood-free inference. A related but different idea is to use Bayesian optimization to explore generally this parameter space. So that's Bolfi, Bayesian optimization for likelihood-free inference, and I'm going to talk about that a little bit. So that's for the first scenario. The second scenario is if we try to be a little more agnostic than working in specific cosmological models. So we try to work with something which is model independent as much as possible. And the typical way to do that would be to parameterize the theory as the primordial power spectrum. which under some weak assumptions, so basically just Gaussianity and isotropy, contains the full information. So in this case, if we are dealing with a full unknown function, so it means that we need of the order of 100 to 1,000 dimensions to describe such an unknown function. So in other words, we try to address much higher dimensional problems than what we can do with likelihood-free rejection sampling, which will fail in more than a few dimensions. So this is the number of parameters route. So the price to pay for that is, of course, that we need much stronger prior constraints in parameter space. The good thing is that this scenario is actually fairly common in cosmology. For instance, if we take the results of Planck series, then I want to argue that we do not need a very general machine to deal with Euclid data, but we are only looking for actually small deviations around the Planck fiducial values. So in this case, a successful idea will be to expand the simulator in parameter space around some expansion point, around some fiducial point. So an algorithm that I call simulator expansion for likelihood-free inference, which makes it selfie, of course, which I found fun. And I swear I thought of that name after developing the method. So let's first talk about the number of simulations routes with Bolfi, with Bayesian optimization. So here is a cartoon of how Bayesian optimization works in a general context. So we are trying to learn some target function here, which would be the distance between simulated and observed data. And we need two ingredients for that. So the first one is a regression of the distance between observed and simulated data, which is sampled by these simulations in parameter space. So a good way to do that is Gaussian process regression, actually, which gives both a predicted mean and a predicted variance, so an uncertainty on this prediction. So that's the first ingredient. The second ingredient is a so-called acquisition function. So this is user-defined. The acquisition function essentially captures the utility of the next simulation in parameter space in order to optimally learn the target function. And what you do at every step is to maximize this acquisition function and to run the simulation at the maximizer of this acquisition function. So this has been studied in a more generic case for Bayesian optimization with some known acquisition function to optimize function. What you should use as an acquisition function for approximate Bayesian computation may not be obvious at first, but it turns out, in fact, that the optimal acquisition function for approximate Bayesian computation can be written down analytically. And it's called the expected integrated variance. For lack of time, I'm not going to show the analytic expression, but you can find those in these two papers, depending on whether you work in the non-parametric or in the parametric approach. So results based on that. With Bolfi, I reanalyzed the supernovae data, which is a well-controlled problem in cosmology, so the JLA supernovae sample. So the goal is to get this yellow banana here, which is the posterior on W and omega m, two cosmological parameters. So the outcome is the following. So this is what you can get with likelihood-free rejection sampling with a reasonable threshold, and that was about a few 100,000 simulations. And in red, you have the outcome of Bolfi for just 6,000 simulations, as compared to the cost for the MCMC here to get sufficient convergence was about 6 million evaluations of the same model. So the key message here is that we can reduce the number of simulations quite a lot. Actually, the number of required simulations for inference will be reduced by 2 to 3 orders of magnitude, depending on the model. So now comes my call or maybe challenge for the simulators in the room. We have a need in data analysis for cheap models that we can evaluate a few thousand times. So this would not be the full Euclid flagship simulation, for which we have one realization. These wouldn't be very cheap data models that we can evaluate millions of times in a laptop, but it's in this intermediate regime here of a few thousand times that we can afford.
Can you explain, I know there's some difference depending on this left and right plot, and why the contours are utterly different?
Yes. So, I'm sorry? Well, the green is more conservative. The green is more conservative, and this is because we have a threshold between observed and simulated data. So likelihood-free rejection sampling, if you have a finite threshold epsilon, will make you more conservative. So you'll always have inflated contours. In the case of Bolfi, so you may notice that you have slightly smaller contours, and this is because of the limited number of simulations. So I have only a partial marginalization over the nuisance parameters of the problem. So A few comments on the number of parameters route. So the idea of expanding the simulator in parameter space. So the framework is to work with a Gaussian prior and a Gaussian effective likelihood. These would be the assumptions here. And as I was saying before, so we linearize the black box around an expansion point in parameter space, so typically Planck fiducial values. So first order Taylor expansion here. So we have the fiducial point and the gradient of the data model around that point, which we can evaluate by finite differences in parameter space. And the outcome of these two is that under these assumptions, actually, the posterior takes also a simple form. It's a Gaussian first. And here are the mean and variance, which involved so the observed summary, some prior covariance, the gradients of the black box, which were here, and the covariance of summaries. So this is very analogous to a Wiener filter, actually, where this takes the form of the pseudo signal for the Wiener filter, and this would be the likelihood part, which takes the form of the noise, essentially, for Wiener filtering. So that's the analogy. It turns out that all the quantities that appear in this equation can be evaluated through simulations only. And in fact, the number of required simulations is even fixed a priori and can be run on different machines. Now, for a proof of concept, I applied this to my own black box, my own simulator, which I called SimBelmune for reasons that are beyond the scope of this code. So any individual ingredient in this code can be that you have codes on the market to compute those with higher accuracy, but I put everything in the same framework here as required for likelihood-free analysis. So the first ingredient is a dark matter simulation, which I do with the first implementation of COLA and the spatial extension, SCOLA. And downstream, all the survey simulation with all the observational effects, so redshift space distortion, bias, selection, and instrumental noise. The outcome of this, so this selfie method and this black box that I just presented, is a reconstruction of the primordial power spectrum. So we are particularly interested in reconstructing BAOs, of course, baryon acoustic oscillations. So we started with a prior which does not include these oscillations. The ground truth that I'm trying to reproduce is in blue. And as you can see, we'll have with that non-biased reconstruction of this function. So these are here 100 parameters which are dealt with simultaneously. And to my knowledge, no other likelihood-free method can deal with such a number of parameters. Also, another comment is that we can compare to the state of the art, so that is the Bohr's collaboration. And typically, they stop their analysis at 0.3, thank you. And in this case, I've been able to use all the modes up to 0.5. This is because I rely on a full numerical model, which I can trust to these scales. So that's a factor of, since it's scaled as case cube, it's a factor of 5 times more mode that go into the analysis. Also, this is just for 1 gigaparsec cube, and of course, we'll have much more potential with Euclid data. So I'm just flashing this. Based on the primordial power spectrum and the linearized data model, we can recover cosmological parameters by just adding a layer to the Bayesian hierarchical model. And this is robust to phase and noise realizations. I'll make this code publicly available. This doesn't require any more simulations. It's a post-processing step. So I'll make this code publicly available soon if anybody is interested, and I jump to my conclusions. So my goal was to develop and use algorithms for targeted physical questions that allow the use of simulations that involve, in particular, all the relevant physical and observational effects. So the outcome is that Bayesian analysis of galaxy survey with fully nonlinear numerical black box model is actually not an impossible task. So depending on the problems that we are dealing with, 2 routes, the number of simulation routes, where we can reduce the number of simulations by a few orders of magnitude, and the number of parameters routes, where we can address higher dimensional problems with a fixed computational workload, which is also perfectly parallel. Thank you.
Thanks a lot, Florent. We will have time for 1 or 2 questions. Over there.
So you showed an example of Bayesian optimization and you applied it to the JLA supernova. So how much time does it take compared to traditional methods to make the contours? Is it faster, slower?
So the simulator in this case is the same as what goes into the MCMC for supernova analysis. So I'm just comparing the number of evaluations instead of wall clock time. But the number of evaluations for MCMC would be about 6 million to get proper convergence, and with Ball physics was 6,000. So it's a reduction by 3 orders of magnitude.
From Shirley here.
This is a quick question for the JLA analysis. Your contour is smaller, right, than the MCMC contour. Do you have any idea why that's the case?
Yes.
And if you redo this with, what Adam Rees is claiming, does that mean we have a stronger tension?
Yes. So first comment is that only the 3 sigma contour is actually substantially smaller, and in most cosmology papers, the 3 sigma contour is usually not even shown. Now to answer your question, we have slightly smaller contours, and that would be because we have only partial marginalization over the 4 nuisance parameters that appear in the problem. But you can correct that by just throwing more simulation into the code, actually. So it's a trade-off between this small bias and the number of simulations.
Okay. Thanks a lot, Florent. And we now have Robert Lillo, which will tell us about structure formation in dark and bionic matter with kinetic field theory.
Oh, sorry.
Mm-hmm.
She's going to warn you at 5 minutes before the end of the talk, and you have 15 minutes. Okay?
Very good. Okay, can you hear me? Good. So hello everyone, and thanks a lot to the organizers for giving me the opportunity to talk about this project. So I'm currently a postdoc at the Technion in Israel, but this is work that I worked on already before. I began before doing my PhD with Matthias Bartelmann in Heidelberg and different other people from his group. So after we talked a lot about already different simulational approaches to structure formation, what I want to do now is present a new analytic approach to this problem, and also how to deal with dark as well as baryonic matter in this approach. So I want to start with a short motivation why I think such an analytic approach is needed, in addition to what we already have. And then we'll explain shortly the basics of the formalism, how to apply to dark matter, and then lastly extend this to the case of baryons. I mean, I don't think I have to tell too much about this slide. So we all know next surveys will probe smaller and smaller scales, megaparsec and below at % precision. And it's of course marvelous because on these small scales where structures evolve nonlinearly, there's just a wealth of statistical information that just waits to be extracted and interpreted. However, of course, we need, as you all know, precise as well as accurate theoretical prediction for this. So we learned a lot about precision already. What I want to focus here is more on the accuracy part. And specifically what I want to look at is an analytic approach that is as accurate as possible to get the structure formation from the time of CMB decoupling until basically nowadays, the nonlinear structures we see today. And since we already talked about a lot of challenges, I think there are many challenges, obviously. We heard about a lot. I want to focus on 2 that are really concerning dynamics themselves of the structures, of the matter we see. One is very simple. Dark matter is, as far as we know, collisionless, as always nicely illustrated by our all-time favorite bullet cluster over here. And while this makes your life, on the one hand, easier, so just, quote-unquote, have to be concerned with gravity, it also means that dark matter particles, streams of dark matter particles, are free to cross each other, and this will happen on these scales that we're talking about. This is the multi-streaming regime of dark matter. So the conventional analytic approaches, like the fluid Eulerian approach or Lagrangian approach, will break down after this crossing of streams. So for Eulerian, because the velocity field is not unique at this point anymore, which you need for the fluid equations. And for Lagrangian approach, the problem is that the mapping in configuration space is not unique anymore as soon as you can have particles at the same position. So, and body simulations, of course, get around this by treating everything in the full phase space, where trajectories do not cross. and take into account the full particle dynamics. But of course, well, they are expensive, especially if you want to cover large parameter spaces, extract higher order correlators. And in addition, I would definitely argue that you have more potential of gaining a deeper understanding of structure formation in an analytic approach compared to an embodied simulation. There's kind of an intermediate regime nowadays. It wasn't talked about yet, I think, in this conference, effective field theory, which essentially takes a Eulerian approach for an effective fluid, including higher order effects, but needs an input from simulations for small scale effects to fit these. So what I would argue is there's still need right in the middle of this for a purely analytic approach that deals with these dynamics, collisionist dynamics, completely correctly. So referring to what Roman said, basically trying to push from the analytic side a bit further into the nonlinear regime this way. Second of all, which was already alluded previously, is of course in these small scales, baryons have to be taken into account. And as Roman already said, this can get very, very messy, very complicated. So I'm not claiming that, I'd say claiming that an analytic approach is able to tackle all of this would be very bold, to say the least. But especially if you consider astrophysical feedback. But what I want to show here is at least how you can include some of these effects that should be able to help you in the onset of these baryonic effects. Specifically, I want to look at how to include the effects of gas dynamics in comparison to the collisionless dark matter. All right. Right, kinetic field theory. So in its essence, statistical field theory approach for classical particle dynamics in phase space, as I said. So one by one. In phase space means the fields in our approach are not densities, not velocity fields, not macroscopic quantities. They're actually positions in phase space of a set of an arbitrary number of particles. They have to specify some initial distribution. Then rather than evolving densities itself, actual particle trajectories are evolved, and whatever desired quantity you want, like a density correlator, you evaluate in the end. So for dark matter, we are here in the regime where they are conservative regime where non-relativistic. These are just described by the Hamiltonian dynamics, so Hamiltonian equation of motions, where for Q a co-moving coordinate, the free Hamiltonian is just the sum over momentum squared with a scale factor squared here, and V is just the gravitational potential that has to be evaluated between all pairs of particles. Now, obviously, if you would actually track all of these individual trajectories, we would be back to embodied simulation. That's not what we do. That's not what we can do. But what we're interested in is the statistical information of this, and this makes us manageable. So what I set up is many statistical approaches to the partition function for this approach. Essentially, all of this just describes sum over all possible trajectories in phase space, given some initial distribution of all these, but only take into account those, which is this delta function, which satisfy the equations of motions. It's deterministic after all. And this is just a neat way to express this in a field theoretic way. And shorthand for me would just be there's some action describing the equation of motion and some trace concerning this path integral. And the initial conditions we use is, so we assume some Gaussian initial density and momentum fields that are correlated, and there's some Poisson sampling to get your initial distribution of particles. This is all encapsulated here. Now, as I said, what we're interested in, even though we want to concern us with the macroscopic dynamics, are still macroscopic information. So, for example, correlators of a density. A priori, density in our formalism is really a sum of individual delta peaks at the particle positions, and a correlator where you have to perform this trace over operation over the appropriate number of densities. So, due to the fact that we have some initial probability distribution here, this still becomes, there's some effective coarse graining, so to speak, to get some smooth results for our correlation functions. That's just formally. And the question is, of course, how do you deal with this in practice, because interactions are very, very nonlinear here. So we split the equation of motion just into a linear and nonlinear part. Linear part naively would be just a free motion, so ballistic trajectories and inertial trajectories in physical space, plus Newtonian potential. But it's actually also perfectly possible to take as your linear solution already a Zeldovich trajectory, which gets you further into the further into the small scale regime, and then can exactly find an effective, so to speak, residual interaction potential relative to these trajectories that you consider. Then the linear part is straight trajectories we can solve exactly, so the exact expressions for how the correlators evolve given these linear equation of motions. But we have to deal in some approximative way with the interactions. I've worked on different approaches so far. Most naive one is taking this action that was part of the partition function and expanding it perturbatively just in the interacting part, or doing some resummation of these. Another approach is to find some approximation in the exponential itself without expanding this perturbatively. For example, the Born approximation, meaning we're evaluating forces along unperturbed trajectories, or the one that I will show you results today is replacing the force in there by some suitable average. By average, I mean not actual average of a force in a particle, because this would vanish in our statistically homogeneous system, but it turns out it was inspired, if you look at the perturbative expansion, what you can do is take like an average effect of a diff on a specific Fourier mode. So the effect of an interaction, the potential gradient given Fourier mode can be approximated by a weighted Fourier transform, where we here put in the correlation function. So basically the probability of finding two particles in a different position. So rather than concerning us with the exact position of the particle, we have this average position of these and average over this. And what we find is in this approach the power spectrum compared to halo model fit simulations. And we see going down to very small scales, we follow this very closely, but of course log-log plot hides a lot of things. And so what I'm showing here as well is the relative deviations. So as you can see, in intermediate as well as even a smaller regime, the deviations can be of order 1, but up to also 10-ish%. So while this is the first result. I'm very happy with this. It's very promising. I have to acknowledge that we have to go to higher order corrections to really reach the precision we need. Secondly, baryons. As I said, baryons follow gas dynamics. So while you could describe this Hamiltonian approach, it would be very hard. So in this case, we actually go to fluid equations, the Euler equations for mass, momentum, energy conservation. But since we want to couple this still to our point-like microscopic dark matter particles, we want to treat these also in a particle approach. And again, get some inspiration from simulations and do a smooth particle hydrodynamics-inspired approach, meaning we divide this fluid into small mesoscopic effective particles, small fluid elements, which each carrying some information like the position, velocity, and this internal thermal energy. And then the macroscopic quantity is some smoothed average over these. And this allows us to find equation of motions for these particle quantities. What you can do then is some consistency check, just here for self-gravitating adiabatic gas, just in the static spacetime. It's completely analytical. And then the transfer functions, so the change, the normalized power spectrum over time actually shows a strong increase on small scales of gravity and oscillatory sound wave behavior on small scales, and actually can check analytically that the correct Jeans length between these two regimes as well as the correct sound speeds is reproduced. So what we're actually interested in, of course, is the coupling of dark matter and baryons. And so far this is very preliminary. So we're looking here at a very simplified case. Of course they are fully coupled by gravity, but we're only considering same initial Badinat power spectrum for those, because we're only concerned with dynamics at the moment, and also ignore the temperature fluctuations. So just assume every particle, every gas cell has an average temperature that's adiabatically cooling, so the pressure can be related to the density itself with this mean temperature, which then allows you to decouple the energy equation and just be concerned with positions and velocities of these particles. And what I'm showing now is just, first of all, just linear evolution in this case. This is the relative deviation of this coupled system to the pure dark matter case, where this is the baryon, these are dark matter, and black is the total spectrum. And as you would expect, baryons, due to their pressure, get a suppression on small scales. But also dark matter does because it's coupled gravitationally. Yes. For comparison is a result of hydrodynamic simulation, including these adiabatic gas dynamics. And up to like K roughly 1, qualitatively, the behavior is the same. You get a suppression mostly in baryons, only tiny effects in the dark matter. But then from then on, we have completely different behavior. They are well, first of all, because they have nonlinear effects, which are not included here. Second of all, these also take into account effects of energy transfer between dark matter and baryons, which actually allows to the dark matter, which is the dashed line here, to fall quicker into a potential well than it could without baryons. So basically, heating up the baryons this way, falling quicker in the potential well. In our simplified model, this is of course not included. So more than this behavior up to K equals 1 should not be expected at this point. Yes, so I already come to my conclusions. I think I could show you that this kinetic field theory approach is able to describe the collisionless dark matter dynamics fully consistently far into the nonlinear regime. However, at the moment, we're still considering this precision cosmology era, still lacking some precision in these scales. So obviously, we have to go to higher order corrections. A vague idea could also be to combine these effective field theory approaches rather than fitting those to simulation results. Maybe, since we have a consistent description up down to small scales, combine these with KFT results. And secondly, it's possible to include gas dynamics into this approach consistently. And the very first results, linearly evolved coupled system with simplified gas dynamics shows qualitatively good behavior up to intermediate scales. But obviously, we need to implement the full adiabatic gas dynamics for the coupled system, which is currently ongoing, and then also go to higher order corrections. Thank you.
Thank you, Robert. Questions? Ruth?
Sorry. How much better is this kinetic field theory result which you showed, which had like 10%-ish deviations in nonlinear scales to, for example, second order Lagrangian perturbation theory?
Right now, it really depends.
Yeah, the n-body part.
So going to smaller and smaller scales, the KFT, at least in this approximation approach, gets better, or at least comparable or better, it seems. So I mean, it's the question about how far you can trust these. Unfortunately, what is still my biggest concern is why we're on these mildly nonlinear scales we have this larger deviation. Honestly, it's not really understood for us. So we have to go to higher orders, maybe by some bootstrapping of this approach to see if this can be reduced. So right now, we're still lacking in this region compared to other approaches. So, but the aim is to be consistent up to high K. That's basically the starting point of this approach.
So if there's no other question, I propose to thank again Robert. And I'll ask Matteo to come forward. And Matteo Cataneo is going to tell us about modeling the nonlinear clustering in beyond the lambda CDM cosmologies.
Let's see.
Okay. Matteo, you have 15 minutes.
Okay.
One you and you only have 5 minutes, and then one.
Okay. Sounds good. Can you all hear me well? Yeah, maybe. I don't see anyone nodding, but okay. All right. So first of all, thanks to the organizer for having me, and good morning, everyone. I'll follow on Robert's footstep, and I'll talk about predicting, in this case, the nonlinear meta-power spectrum for cosmologies beyond lambda CDM. So this is a work that appeared in these two papers, one last December and one more recently, this month. And there are two upcoming papers this year. I don't know exactly when, but stay tuned. It's going to be in the next few months. This is a list of all my collaborators. And before I start, let me tell you that as an Italian living in Edinburgh, it's really a shame to tell that I'm missing Scottish weather at the moment. It's really, really hot for me. I got used probably to the northern latitude weather, but yeah, that's exactly what it looks like now. So let's move on. So the first question you might ask is why going nonlinear at all? And I think we got very good answers and very good introductions from Clement and from Robert as well. So basically, this is just a reiteration of what they just told us. So we know that at the level of precision, future surveys like Euclid and LSST will reach something like 1% precision on measurements of the large-scale structural observables, for example, the cosmic shear power spectrum. And this requires actually, so this kind of quest for going nonlinear is really data-driven, and this requires, of course, modeling from us theorists and phenomenologists modeling these kind of scales to that level of accuracy or better. And you can see here in the top panel of this figure, this summarizes actually the amount of information that we can gain going from linear scales to nonlinear scales. This is the signal-to-noise ratio for the convergent power spectrum in, I'd say, GR in this case. So you can go from linear to nonlinear. You have a tenfold increase in the amount of information per mode. So this is a huge amount of information we can get. This can be used to improve our knowledge of the standard cosmological parameters, to break degeneracies, but even more importantly, if you look at the lower panel, to actually investigate extension to the lambda CDM models. So in this case, you can see the convergence power spectrum ratio of some modified gravity model to GR. And there is one particular model, for example, here, that due to what is called screening mechanism, basically it's non-detectable. There is no detectable deviation from GR down to very nonlinear scales, and then you see something down there. So we really need to go down there to see these kind of models, which are the viable models at the moment. So what would you like to have as for a method to predict these things? So they must be fast. This kind of method to predict the nonlinear power spectrum must be fast because we have to evaluate this quantity hundreds of thousands of times. And so it has to be like a level of milliseconds, some like fraction of seconds for sure, if we want to do this in a reasonable time frame. It has to be accurate, as I showed you in the previous slides. And of course, it has to be flexible if we are to explore extension to lambda CDM. So for example, modified gravity dark energy, other dark matter candidates, massive neutrinos, affected relativistic distribution, and so on and so forth. So what's off the shelf that we can actually use right now at the moment? Basically, there are 4 different approaches. You see there is a blind spot here, like a blank spot. There will be another one that I add later. So we have the Halo model. We have fitting functions like Halo fit and HM code, emulators, Cosmic Emu, Euclid emulator that Roman introduced, perturbation theory, SPT, RAGPT, FT of LSS, and all these kinds of things. But none of them has these 3 qualities simultaneously, right? Possibly, kinetic field theory has these things, but it's not off the shelf. So we cannot use it at the moment, as we heard. They might need to go to higher order corrections, so I just say possibly. I take a different angle. My approach is a bit different, and basically the idea is to use what you already have and combine them in a very different way. So we start with perturbation theory and Halo model, and then we add some sort of emulator. I'll show you in the next few slides. I split the talk in 2 parts. So the first part will be about perturbation theory and Halo model, and then the emulator in the second part. And this is what I call the Halo model reaction framework, which I claim is fast, accurate, and actually flexible. And there are some free parameters, it's true, but these are not directly fitted to the observable you want to predict. So if you want to predict the nonlinear matter power spectrum, I'm not fitting these parameters to the nonlinear matter power spectrum from simulations. This will come from priors, from external data. For example, you'll see the Halo mass function, the cluster abundance, or the dark matter PDF. So there will be external data that inform you on those parameters. You can then predict, for example, cosmic shear. So there will be a crosstalk among all these kind of observables. So first of all, what's the Halo model? Halo model, I guess most of you know. So this is the kind of picture we have of the universe in the cosmic web. We have filaments, clusters, sheets, and voids. And in the Halo model, you assume that all dark matter, all dark matter in the universe is confined into these structures called halos, spherically symmetric and hard, so they cannot compenetrate. They are mutually spatially exclusive. So this is the kind of picture you have in the Halo model paradigm. And then say you want to predict some statistics that informs you on the spatial distribution of the matter in the universe. So in this case, of the halos. And then you need to, for example, compute a correlation function, or it's Fourier transform of the matter power spectrum. And this can be done in the Halo model framework, splitting the information in two parts. One is the two Halo term, where we look at correlation between halos, different halos, and the one Halo term, where you look at correlation within the halos itself. So the first part will be described quite well by quasi-linear perturbation theory. In the second part, you have information about the abundance of halos, so the Halo mass function, the size of the halos, the virial radius, and the profile, which I assume to be an NFW spherically symmetric profiles. So Halo concentration in that case. So some of you may say, okay, why are you using the Halo model at all? We know that it doesn't work for these things. So for example, you can compare the prediction of the Halo model to a simulation. You can see this is a work by Massara et al. In 2014. There are the two contributions, one Halo and two Halo. And when you compare the Halo model prediction to the simulation, you see that there is a discrepancy of up to 20, 30%, depends on redshift, compared to the simulation. And we are talking about precision accuracy cosmology, right? So you say, okay, Halo model is dead. Not quite. If you follow a three-step process, this is the first one, you can actually save the Halo model. So the first one is defining a pseudo-cosmology. What is a pseudo-cosmology? It's a lambda CDM cosmology with initial conditions that are adjusted in such a way that the linear matter power spectrum of this cosmology at the redshift you are interested in is exactly the same to the linear power spectrum of your real cosmology you're interested in. So say you have a WCDM cosmology, you will match the linear power spectrum of your pseudo-cosmology, which is a lambda CDM, to that one. So since I think a picture is worth 1,000 words, and the sequence of pictures is even better, I do that. So you start with this cartoonish figure at, say, redshift 100. Then you have your pseudo lambda CDM power spectrum and your real one. So they will start from different amplitudes. In this case, for example, the real cosmology is cosmology that only changes the growth of structure in a scale-independent way. So there will be just an amplitude shift. So they start from different initial conditions, the amplitude. Then you let it evolve. Redshift 1, the two will be less discrepant. And then at redshift 0, which is your redshift of interest, and in this case, the two will match. It's as simple as that. And now, this is the tricky bit. So you use this pseudo-cosmology to define what I call a reaction function, which is the ratio of the nonlinear matter power spectrum in your real cosmology, your target cosmology, to that of the pseudo-cosmology, a lambda CDM-like cosmology. And I predict this using the Halo model. So I split it in one Halo and two Halo term. So of course, the two linear power spectrum are identical by definition. And there is a pre-factor here, which is a correction factor. There are two free parameters. I chose that functional form because it works quite well, but if you find something that works just as well, you can use it. These parameters are not free, and they come from perturbation theory and the Halo model itself. All right, so you can, I'll tell you how you compute this. Perfect, so if you look at this, again, this cartoonish picture here, this is the action function. The red one is a typical shape you might get. On very large scales, it will converge to 1, hopefully, because the pseudo and real cosmology have exactly the same linear power spectrum. And then you will have deviation due to nonlinearities, basically coming from the one Halo terms ratio on very small scales. And then there will be a transition region, which is captured very well by this prefactor if there are screening mechanisms, for example. So the prefactor is actually a correction factor for screening mechanisms like the chameleon screening. If you have Weinstein screening, for example, this is not required almost. And if you have dark energy, you don't need it at all. If you have massive neutrinos, you don't need it either. All right, I need to move fast. And then the third step, you start from assuming you have this nonlinear multi-power spectrum that is coming from some, say, cosmological simulation, nonlinear simulations, or some emulator. Then you can multiply that by the reaction function, and you get your nonlinear multi-power spectrum for your target cosmology. Okay. I apply this to modified gravity theories, to dark energy theories, and massive neutrinos so far. And you can see here an example. So these are two different redshifts in different colors. The predictions are the blue and red lines. And below in the bottom panel, you see the accuracy of this method. It goes down to k of 1 at least, with an accuracy of 1%. All right? And here, my pseudo-cosmology reference power spectrum is coming directly from the simulations. All right? So we need to find a way to actually compute this independently. And I'll show you how you can do that. I applied that to NDGP as well. So this is a kind of different modified gravity theory. It's scale independent. F of R is scale dependent. The screening mechanism is very different. One is Scale-Million, the other is Weinstein. So it works just as well. For evolving dark energy, all I'm showing here, I'm not using simulations. This is the cosmic emulator. I'm using both the emulator for the real cosmology and for the pseudo-cosmology. And I can show that within the same emulator, I can move to a cosmology that is not lambda CDM. And that can actually do better than the emulator itself, because there are problems due to the domain of validity of the emulator, so I can push the boundaries even further. And for massive neutrinos, things are brilliant, actually. So we can actually predict the nonlinear multi-power spectrum from different neutrino masses down to k of 10 with, with accuracy of 1% with this approach. So now you might ask, so how do you actually compute the nonlinear multi-power spectrum for the pseudo-cosmology? Well, you can go like using the emulator. So again, the pseudo-cosmology lambda CDM cosmology. So this will be a lambda CDM emulator. And if the only model you're interested in are scale-independent modification of your lambda CDM cosmology, then you can use, for example, existing emulators, right? Cosmic Emu or the Euclid emulator. This depends on 5 cosmological parameters, and all you need to do is to adjust this AS, the amplitude of the multi-power spectrum. But most of the model we're interested in will introduce some scale dependence. So there is more degrees of freedom beyond the 5 cosmological parameters. So you have, say, the amplitude of the scalar field, massive neutrinos, combination, and effective, all these things. So for example, we investigated the ratio of the linear power spectrum, for example, for some extension to lambda CDM cosmology, for gravity, massive neutrinos, and combination, because massive neutrinos for gravity can be degenerate. And you get this kind of shapes. So now would you say, OK, now I can train my emulator on these sort of shapes. Right, but then you are tied to these shapes, right? You don't want that. You want to be as general as possible. So what we do is that we reconstruct the shapes. So we go from these physical parameters, pi x, to some weights. So we do a PCA reconstruction of the shape. We only need 8 weights, which are shown here. And I can tell you more later after the talk how we generate these. But we can reconstruct the shapes at sub% level. So we have delta alpha. These are 8 additional shape parameters on top of the 5 cosmological lambda CDM parameters. So a total of 13. We trained our emulator with 500 nodes. So in principle, you will need some sort of like 1,000 simulations. It's beyond a factor of 5 more than what Romain told us before, but I think it's still doable with very fast simulation codes. We use Gaussian processes, so this is something that we can improve. And you can show here that for the nonlinear power spectrum of the pseudo-cosmology, we can reach % level or 2% level accuracy, okay? This is using HaloFit, actually. So this is a proof of concept emulator. We don't have a real emulator at the moment. And also for an effective, this is a very large and effective, we reach similar level accuracy. So to conclude, I hope I convinced you that the Halo model reaction framework is actually fast, accurate, and flexible. So we will be releasing a code soon in the next few months called React, for lack of imagination at the moment. And it takes 0.1 seconds for a single redshift, so it becomes doable to compute the cosmic shear power spectrum within a few seconds, comparable with CAMP. And in the future, we'll hope we can improve the highly nonlinear regime for modified gravity theories. You saw that there are some discrepancies down there. For the pseudo-cosmological emulators, we are looking for simulators to jump on the bandwagon here and help us running and building the emulator itself. We can improve things actually using sparse polynomial case expansion or looking at different optimization for the experimental design that you use for the nodes of the emulator. Of course, we need to think about how to include baryonic physics. I think it's possible within the Halo model, using similar things as Schneider et al. Possibly extend this to galaxy clustering, galaxy-galaxy lensing, so we can do 3.72 correlation function analysis. I think it's possible not just to focus on particular modified gravity theories, but at least a subclass of Densky theories. This is applicable. And with this, we can actually look at degeneracies between different physics beyond MCDM, for example, massive neutrinos modified gravity. Thank you, that's all.
Thanks also for this talk. Questions from the room? I actually have one. So it's not only a question for you, but probably for the other emulators or fast simulation we had today, which has been answered partially by Shirley. My question is about higher order moments. So have you looked into that? And
not yet, not yet. And the fact that we are matching the linear metapower spectrum doesn't convince me that we can go higher order and apply the same kind of formalism. It works for Halo mass function, for example. The pseudo and real actually are very, very similar. So this is the reason why this approach works very well, but not higher order moments for now. There are people working on bispectrum, I think, but in Geneva.
Question here?
Sorry, 1% precision that you mentioned is up to which K?
The percent level.
Yes.
So it's a K of 1 at the moment. It depends on the model. With massive neutrinos, you can go down to K of 10.
K of 1 is highly nonlinear. Is it possible to gain 1% precision at that K? I mean, we don't know bias.
This is metapower spectrum. So this is particles, right? It's not galaxies or halos.
Oh, okay. Sorry. Okay. Now it makes sense.
Yeah.
Okay.
My fault.
We take one last question and asking
Yeah, thanks. Great talk. So for this React code, you will already have built the emulator itself, or is this just?
No, this will be built in within Cosmosis.
Okay.
And as a standalone code, and it will be coupled to HM code for now. That's the only code that can do this sort of things at 5% level precision.
Okay, so you will use that as like the true model for the moment.
Yeah,
HM code.
I mean,
Okay.
we cannot do better than that for now.
Okay, but so you plan to do a real emulator by like looking at 6 parameter space?
Yeah, if simulators help me, yes.
Okay.
It's hard to convince them. Okay.
Okay, I'd like to thank once more Matteo. And we'll have our last talk of this morning session from Pravabati Shingangbam, I hope I pronounce it correctly, who tell us about Minkowski tensors as new statistical tools for analysis of cosmological fields. So it's right down on the higher order moments question.
Okay, so I want to thank the organizers for giving me this opportunity to share my work. So I am going to switch gear because I have not heard the topic of the geometrical and topological properties of cosmological fields being discussed in this conference so far. Specifically, I am going to talk about quantities which we have recently introduced for cosmological analysis called as Minkowski tensors. So I should mention that we have this team of people with whom I have been working on this for the last 2-3 years. The first row are my students, and I will mention applications on cosmology, work done by Joby, Akanksha, and Priya is in the audience. And Stephen is the postdoc at KIAS, Changbom Park, many of you may know him, and Yogendran at IISER Mohali. Okay, so just to give to put things in perspective, when we have random fields, we can have excursion sets, which are like level sets. You split the field into different levels by choosing different field values, and you look at the spatial regions where the field has values higher than or equal to the particular value that you have chosen, the threshold that you have chosen. So in 2 dimensions, you can have, as you increase the threshold, as you vary the threshold, you can have different subspaces of the space that you are interested in, 2-dimensional space. So you have this very beautiful connected regions and holes, and there is very intricate structure, but the boundaries are very intricate and so on, and so various quantities can be constructed to study the field like this. Similarly, in 3 dimensions, we have again excursion sets, so these are called excursion sets, and so the point to note here is that there is rich geometry and topological structure. So this topic has been applied in cosmology quite a bit over the last several decades. Of course, one can ask why should this be interesting. So we all know that if you believe in inflation as the source of the primordial perturbations, there should be cosmological observables are random fields. They start out possibly as Gaussian fields, and then they get modulated by the physics that happens at later epochs. And many properties of Gaussian fields, we can have a good control over the analysis because we can calculate them analytically. And then these quantities, of course, they contain all orders of endpoint functions, and so this is complementary to endpoint analysis. Okay, so what are the mathematical tools when I say geometry and topology? So in the literature, one can find 2 different ways of doing the analysis. One uses something like Morse theory, for you start with functions, look at various peaks, maxima, minima, saddles, and then you infer the topology. So there are various applications of this in cosmology. So I will not be, I'm not an expert on this, I will not be focusing on this, but I will be talking about integral geometry. So the specific quantities in integral geometry are quantities like the scalar Minkowski functionals. So usually people have been calling them Minkowski functional. I add the word scalar here because I'm going to generalize to tensors, because these are invariant under translations and rotations. And Betti numbers, which are structure counts. So these quantities are physically very simple quantities. They are volumes, boundary, contours, or in 3D, they are surface areas and structure counts. So there have been many applications of this over the last several decades. Mainly, the main application has been in primordial non-Gaussianity searches and so on. So now let us go beyond that, some more integral geometry. So there's our Minkowski tensors, and the main information, as I will explain in the next couple of slides, is that we get information about anisotropy and alignment of structures. So before I specifically come to the quantity of interest, let us take a look at what is tensorial Minkowski functionals are. So I'm going to specialize, because I have very little time, I'm going to specialize to 2-dimensional fields, and we have done work on 3-dimensional fields also in large-scale structure, but I'll skip that for the purpose of this talk. So when I have an excursion set, so these contours here are labeling, they are, the colors are different boundary contours of the excursion sets at different thresholds. So you can see very nice, very beautiful structure, these are the boundaries. So using this, what the scalar Minkowski functions are nothing but the area which is enclosed by the boundaries, or the boundary length and the counts of the structures, hot spots and cold spots, and if we subtract that, we get what is called the genus. So the tensorial Minkowski functionals, they are, without giving you the formula, they generalize. So I'm going to specify, so tensorial Minkowski functions are a class of mathematical quantities which characterize all morphological properties of structures. So I'm going to specialize to those which are translation invariant. So this is flat space for now. So W0 is, it turns out that there are 3 of them. So generalizing the 3 scalars, there are 3 corresponding ones. So it turns out that as far as anisotropy and so on is concerned, the Two of them are not so interesting. They don't give new information, but one of them gives new information, and I will be describing that. So these are now contained in the tensorial Minkowski functionals as you take the trace and you get back the scalar Minkowski functionals. So mathematically, these were developed about 20 years ago by these people. And so this is for general morphology of structures. Then my student and I, we applied it to random fields, particularly to CMB, and then we generalized it to case of the sphere. So I have already mentioned here that there is new kind of information. So let's go to the definition. Okay, so how do we quantify shapes? So I'm going to be specifically talking only about W1. So I call this as a contour Minkowski tensor. So suppose Q is this, let's take the example of this structure here. Q is the entire set contained in this, and the delta partial Q is the boundary. Then what we define is we can take the unit tangent vector at any point, because it's up to you whether you define this way or that way, and you take the cross product, tensor product with itself, and you integrate it over the entire region. So this is, I'm taking the symmetric tensor product, so it's a symmetric matrix, 2 cross 2 matrix. So what these people, Schroeder-Tuck, did is to define a shape parameter and say that you take the eigenvalues, diagonalize eigenvalues and take the ratio, and we keep lambda 2 to be the larger one. Then this is quantifying it quantifies the shape of this. Of course, we are losing a lot of information about curves and so on, but overall what it does, it approximates it into an ellipse and then says which are the semi-major and minor axes. So this quantity beta shape parameter lies between 0 and 1. For simple cases of ellipse and so on, they can be analytically calculated. So the information contained in beta is that if there is m-fold symmetry with m greater than or equal to 3, then beta turns out to be 1, and if it is not, then it will be different from 1. So beta will characterize the shape. So now in general, of course, I want to apply to random fields, and there will be, I have shown you a slide where there are many curves. And so you can ask the question now, if there is some, for each structure, if you have, there is a direction, then can you define an alignment parameter? So again, this Schroeder-Tuck, what they did is they defined an alignment parameter by summing over all the W's or averaging over all the W's. They are independent, it doesn't matter which one you do because we take the ratio. And we can define an alignment parameter by the eigenvalue of the sum. And again, this is this alpha parameters between 0 and 1. So we can give a geometrical interpretation that this is actually like when you stack, you have a structure and you put them all together because we are using translation invariant, and you stack them. And when you stack them, you can look at the overall structure, which I call a locus curve by the red, and it is alpha is measuring the shape of that stacking. So one can already see that it can be used for various tests in cosmology. So before we do that, let's just see how far we can go for analytic calculations. So W1 actually for all the 3 tensorial Minkowski functionals. For Gaussian isotropic fields, we can calculate analytically what it should be. So this is the ensemble expectation value if you assume that the field is Gaussian. So just to give a detail, you may wonder how from the tangent vector you get the ensemble, it's related to the field, and that is done by taking, so the tangent can be expressed in terms of field derivatives, first derivatives. Okay. So we can calculate this. So Priya and I have actually also calculated for anisotropic, it turns out we can also calculate analytically for anisotropic fields, but I'm not showing that here. So the meaning of isotropy is that this locus curve will be, alpha will give 1. However, when we deal with real data, that ensemble expectation works when we have a almost infinite number of structures. In reality, when we are dealing with finite regions in space, we never have that many number of structures. So it becomes important now in a given space how many structures you are packing in. So it's related to the number of structures that you can pack in. So we computed this using simulations. This is for isotropic random field. Actually, this was done for the temperature field, but the similar thing holds for general Gaussian isotropic field without any cosmology input with some correlation. So this alpha, the alignment parameter, you can see depending on the number, as you know that. So this I am using my field to be normalized by the sigma. So we are counting in terms of mean subtracted and sigmas. So as you go away from the mean, there are fewer and fewer structures. So you can see that the probability that when you have a few number of structures, the probability that they will be very nicely, completely unaligned to each other is very small. And so that is what this is reflecting. And then the shape, this is the average. So at every threshold, you average over, you count how many structures are there, and then you average over the structures. So you can see this beautiful shape which is emerging. So you can go to higher thresholds, and one can see that this going up. So people may be familiar with the work by Doroshkevich and maybe in Born and Evstatiou for two-dimensional fields, that there are predictions for shapes of this. So we have checked whether those formula agree or not, but to 3/4 sigma of the threshold value, with which we usually do our cosmological analysis, actually there is still a lot of deviation from those analytic expressions. And those are very approximate. So this is the exact. Okay, so now I come to some applications. So far we have tested, we have used it to test statistical isotropy with Planck data. This is 2015 data. And then we looked at distortion. So this one is very, very preliminary. I will show you a slide where we have got some distortions, but this is extremely preliminary. So Priya has had a series of misfortunes in doing these calculations. And then I will show about in the epoch of reionization, what kind of physical information we can get. Okay, so that's Joby. So we applied it to Planck data to look for the anisotropy. So basically, we used the FFP8 simulations and the Planck data, and we compare whether to see whether there is whether they are agreeing or not. Okay, so so these are different frequency channels, and since I don't have too much time, the conclusion here is that there is no statistically significant deviation from isotropy. But so we did this analysis at a few smoothing scales, but since then we have learned that if we are looking for something like, for example, hemispherical anisotropy, then we should be looking at smoothing at much higher smoothing angles. So those are things that we are looking at right now. So that's Priya. So now this very preliminary results that we have got is, so we looked at alpha and beta, comparing between using lens peak simulations between lens and unlens. So first result shows that, so the beta, so we found that E and temperature and E, there is small deviation, but it's not so strong, whereas B is very strongly deviated. So the green one is the plot for unlens, and the red is lens. So the result here is that all hotspots and cold, you can see across all thresholds, we are finding that structures are getting elongated. And in terms of alpha, again, the alignment parameter, again, I said that it depends on the number of structures, and so there is deviation at the. So this is, we hope to use it in the future for various cosmological constraints. So it's a goal or a hope. Can I take one or 2 more minutes? Yeah. Okay. So the idea for applying it to reionization is we use 21 centimeter fast simulations. So basic idea is can we get the ionization history? by by putting this Minkowski tensor in some form which is appropriate, and we can extract information. So here the one basic idea is that so this is the ionization field, which starts from 1 and then goes down to 0 as the ionization fraction as it becomes more and more ionized. So you can see that, so just to give you the basic idea, suppose I have two regions where the regions have got ionized. So as ionization progresses, the regions will grow, and then at some point they will merge, and then the whole thing grows further. So you can imagine that if you were asking for, okay, you can have a number count statistics, size statistics, and you can have a beta, the shape parameter. So a shape, you can imagine that this will be highly isotropic, and then it will remain isotropic, and suddenly at this point it will become drop anisotropic, and then it will grow again. So that's the basic idea, and we want to see whether we can obtain this using these simulations. So these are the three things that we measure. So that's what we did. So this is as a function of redshift. So I will not explain the numbers, but this is number count, and this is for different. You just look at the first top slides, top figures. So this is the size, and this is the shape. So the quantity that I was very happy to see was basically the shape. You can see that from very early, this is 18 or 20 redshift. You can see that the shape is becoming, as more and more mergers happen, the shape becomes more and more anisotropic, and at some point when mergers stop, and then the whole thing fragments, and we are left with neutral regions. You can see them. So the ionized regions are only small bubbles within neutral regions. So then you see it growing again. So from here we can extract physical information. Like questions like what is the size to which ionized bubbles grow, when does maximum merger happen, and so on. And so what we have done is so this is the proof of concept paper, and then we have done more work by putting this into the full brightness temperature, which is an observable quantity, and see how we can be constrained. So it turns out that they are dependent on the model parameters. So there will be shift and variations of this depending on what parameters you put in. And so that's the hope that in the future, with future data, this is very, very optimistic hope that we will be able to use it to constrain. Okay, so my last slide is a summary. So I feel that the rich topology and geometry of Cosmology is not fully exploited yet. So this Minkowski tensor, they enlarge the tool set, and I have shown you a few examples where we can get useful information. Thank you.
Thanks a lot.
Questions? Lots of questions. Shirley?
I'm curious, you picked Minkowski tensors, and for some of the cosmological applications, it might be interesting to look at statistics that are rotational and deformation invariant, and I'm curious what your thoughts are on those.
I think it will be very interesting. So I can only tell what are the things that we have applied so far. So apart from this, we have looked at large scale structure. We have quantified redshift space distortion, properties like that. But it is still, there's plenty more questions to be asked. So that is work for the future.
Okay, we'll take one last question because we are all hungry.
So, statistical properties on the peaks in terms of the anisotropy of the CMB,
yeah.
And on even from the like the high peaks seems to be also kind of anisotropic. Is it expected?
I'm sorry, I didn't
like
get
the high peaks when the mu value deviate from 0, it seems they statistically deviate from unity.
From
like
0.
I think the next slides probably shown, not the one. Yeah, this work. Yeah. Yeah. So this curve, it curves down. It seems to deviate from.
Yes. So that is what I explained earlier. I said that. So as you know that as you go to higher or lower thresholds, the number of structures are decreasing. the number of spots are decreasing. So it's related to, alpha is related to the number count of structures, and it is telling, so we know that when you randomly just put, let's say draw ellipses, the 3 ellipses, what is the probability that you will exactly draw it in a way which is isotropic? So that's very small. It's more likely that you will have many other configurations which are non-isotropic, and that is what is being reflected here.
Thank you. Thanks again. And I would like to thank all of the speakers this morning and the students who have given the mics to all the excellent questions. We'll reconvene at 2:10, I guess that's that? Okay. Bon appétit. Thank you.